There is a moment, if you have ever stood far enough from the city lights, when the sky above you stops feeling like a ceiling and starts feeling like a depth. You look up and what you see is not a flat surface painted with points of light. You see something that recedes, something that pulls. The stars do not feel like they are resting on anything. They feel suspended in a volume so large that your mind refuses to fully process what it is doing when it tries to measure it. You stand there small and still, and the universe seems to press down toward you with an almost physical weight of presence, of fullness, of the sense that out there, in every direction, there is something. That feeling, that ancient, wordless sense of a cosmos overflowing with light and matter and structure, is one of the oldest things human beings have ever felt, and it is one of the most profoundly misleading perceptions our species has ever had. What you are seeing when you look at the night sky is not the universe. It is a thin, glittering surface impression of the universe, the way a painting of an ocean is not the ocean. The truth of what the cosmos actually is, its texture, its composition, its architecture, requires you to let go of what your eyes tell you and follow something stranger, quieter, and far more unsettling than the beauty you were admiring a moment ago. This is the kind of investigation that reshapes everything once it begins, and while there is still light, still time, and something rather than nothing, subscribe to Beyond the Universe, because what begins here as a question about empty space ends somewhere much harder to come back from, somewhere that changes the way the word full sounds in your head forever after. Start with the stars. Not the stars as points of light on a dark field, but the stars as physical objects with real separations between them. The nearest star to our own sun, Proxima Centauri, is roughly 4 light-years away. A light-year is the distance light travels in a full year, moving at approximately 300,000 kilometers per second. A beam of light circles the entire Earth 7 times in 1 second. In 1 year of uninterrupted travel at that speed, it crosses a distance of nearly 9.5 trillion kilometers, and the nearest star is 4 of those years away. 4 years of light travel to reach the closest other sun. To cross that gap with any spacecraft humanity has ever built would take tens of thousands of years. The distance between us and our nearest stellar neighbor is not a gap, it is an ocean. An ocean so enormous that the stars on either shore cannot see each other as anything more than points. And yet, Proxima Centauri is close, cosmically speaking, unusually close. The average separation between stars in our region of the Milky Way galaxy is measured in light-years, multiple light-years of cold, empty space between most stars. When you look up at night and see the Milky Way as a band of light stretched across the sky, what you are actually seeing is not a dense clustering of stars as they physically exist in space. You are seeing depth. You are looking through the flat disk of the galaxy, and the impression of brightness comes not from stars that are close together, but from the sheer number of stars stacked along your line of sight, each one separated from the next by years of light travel, all of them compressed by your angle of view into what appears to be a single glowing ribbon. It is a visual illusion created by geometry and by the fact that human eyes cannot perceive distances of that magnitude. If you could somehow remove yourself from the Earth and travel to a point above the plane of the Milky Way, you would look down at a structure roughly 100,000 light-years across and about 1,000 light-years thick in most regions. Within that structure, there are estimated to be somewhere between 200 billion and 400 billion individual stars. But the volume of space those stars actually occupy is almost entirely empty. If you took all the stars of the Milky Way and calculated what fraction of the galaxy's total volume they occupy, the answer would be so small as to be almost meaningless. Stars are like dust motes in a cathedral. The cathedral is real. The dust is there, but the cathedral is not made of dust. It is made of the space between it. This is the first correction, the first readjustment of the frame through which you look at the cosmos. Space is not full. Space is almost entirely empty, even in places that appear from a human vantage point to be dense with light and structure. But this is only the first correction, because once you move beyond the boundary of a single galaxy, the emptiness does not merely continue, it multiplies. The Milky Way is part of a small group of galaxies called the Local Group, which contains roughly 80 or so galaxies including our own, and the Andromeda Galaxy, which is the largest member of the group and lies approximately 2.5 million light-years from Earth. 2.5 million light-years. That number is so large it barely registers as a number. The light you receive in your eye from Andromeda when you look at it on a clear night has been traveling through space for 2.5 million years. It left that galaxy before modern humans existed. It traveled through the void for the entire span of human prehistory and only now reaches your retina. And Andromeda is our neighbor. It is, in cosmological terms, essentially next door. Between the Milky Way and Andromeda, there is not much. There are a few dwarf satellite galaxies. There are stray clouds of gas. There is the occasional isolated star flung out of one galaxy or the other by ancient gravitational interactions. But mostly, there is void. Mostly there is the same cold, unlit, particle-sparse emptiness that defines so much of the cosmos. 2.5 million light-years of it between us and the nearest large galaxy. And beyond that, the next nearest major galaxy is farther still. Now pull back further. Imagine you could rise above not just the Milky Way but the entire local group, and watch it shrink beneath you as you ascended through cosmological distance. The local group would become a faint, loosely organized cluster of smudged light, a few dozen galaxies spread across roughly 10 million light-years. And as you continued to rise, you would begin to see other groups, other clusters, other smears of faint light separated by voids that dwarf the distances you have already tried to comprehend. The local group is gravitationally associated with a larger structure called the Virgo supercluster, which itself contains hundreds of galaxy groups and clusters spread across a region roughly 100 million light-years across. And the Virgo supercluster is itself just one portion of an even larger structure, a vast gravitational complex that astronomers now map as Laniakea, a supercluster spanning approximately 500 million light-years and containing the mass equivalent of 100 million billion suns. You might think at this scale that the universe is becoming more filled, not less. You might think that as you zoom out, you begin to see more structure, more matter, more galaxies filling space. And in a narrow sense that is true, you see more galaxies. But the critical question is not how many galaxies exist. The critical question is what fraction of the universe's volume they actually fill. And here is where the picture breaks down completely. For all its grandeur, Laniakea occupies a finite volume in an observable universe that stretches approximately 46 billion light-years in every direction from Earth. And even at that scale, even accounting for every galaxy, every cluster, every supercluster humanity has ever mapped, the galaxies themselves, the filaments, the walls, the enormous structures that define visible matter in the cosmos, all of it combined represents a fraction of the total volume that approaches something close to negligible. The universe is not, at its heart, a place full of things. It is a place full of nothing, in which things occasionally appear. The exact framing of this takes time to settle, because we are accustomed to thinking of existence as the norm and emptiness as the exception. We live on a planet. We breathe an atmosphere. We are surrounded by objects, by buildings, by biological life that covers this world in such density that it is nearly impossible to find a cubic meter of Earth's surface that contains nothing. Our intuition about reality is calibrated to a world that is, by cosmic standards, incomprehensibly dense. And this calibration makes it almost impossible to viscerally understand what it means to say that the universe is mostly empty, not partially empty, not empty in the spaces between things, mostly, structurally, fundamentally, and architecturally empty. Consider that the average density of matter in the observable universe is estimated to be extraordinarily low. If you were to take all of the matter in the observable universe, all of it, every atom in every star, every planet, every gas cloud, every speck of cosmic dust, and spread it evenly throughout the full volume of the observable universe, you would end up with a density equivalent to roughly a handful of hydrogen atoms per cubic meter, not per cubic centimeter, per cubic meter. A box roughly the size of a large piece of furniture would, in this averaged cosmic reality, contain fewer atoms than you can count on one hand. That is the mean density of the universe. That is what the universe is, on average, made of. A near-perfect vacuum, interrupted only by the rarest concentrations of matter. But here is what makes this so much stranger than a simple statement about density. The matter that does exist, the atoms, the gas, the stars, the galaxies, is not spread evenly through that enormous volume. It is gathered, clustered, drawn into specific regions by gravity, arranged into filaments and sheets and nodes, while enormous regions between them remain almost completely devoid of matter. The universe is not a thin, even fog of substance. It is a foam of structure surrounding bubbles of nothing, and the bubbles are bigger than the walls. This arrangement, matter organized into a vast cosmic web of filaments and walls, with enormous empty regions in between, is one of the most striking features of the universe at large scales. And it did not happen by accident. It happened because of the universe's history, its physics, and forces that remain even now only partially understood. The emptiness you see in the cosmos is not random. It is structured. It is the outcome of processes that have been running since the first moments after the Big Bang. And that is what makes it so unsettling to look at carefully, because the emptiness is not a side effect of the cosmos. In some deeply fundamental sense, the emptiness is the cosmos. When the first deep-field observations from space-based telescopes began to reveal what existed in the tiny patches of sky that appeared completely dark to ground-based observers, astronomers did not find emptiness. They found galaxies, thousands of them in regions of sky that the naked eye would never have identified as anything but void. Each of those galaxies containing hundreds of billions of stars, each of those stars potentially surrounded by planets. And yet, even with all of that, even with the revelation that the night sky is in every direction layered with galaxies stretching to the edge of the observable universe, the total fraction of that observable volume occupied by all those galaxies combined remains almost nothing. Imagine looking at a vast ocean at night. The surface is dark, but here and there, separated by enormous distances, there are tiny islands lit with fires. Each island is rich with life, with complexity, with warmth, and yet the ocean itself, stretching for thousands of kilometers between those islands in every direction, contains nothing but cold water and silence. Now imagine that the ocean is not two-dimensional, but three-dimensional, and that the islands are separated not by kilometers but by millions of light years, and that the ocean itself is not even water. It is vacuum, it is quantum fields, it is a kind of nothing so pure and so complete that it has no color, no sound, no temperature in any conventional sense. That is the universe. The galaxies are the islands, and the void is the ocean. What makes this more than a simple fact about density is what it implies about the nature of reality. We tend to assume that the universe is a place where things exist, where matter is the protagonist of the cosmic story, where the interesting parts, the stars, the planets, the chemistry, the life, are the substance, and the space between them is merely the stage. But this view inverts the actual proportions. The stage is not a backdrop. The stage is almost everything. And the performance, the brief energetic clustering of matter into galaxies and stars and complexity, occupies a fraction of the available space so small that the only honest way to describe it is as an anomaly. And this is only the beginning of what the emptiness reveals. Because once you accept that the universe is not full but instead mostly void, you are forced to ask a question that opens an even more unsettling door. Where exactly is the void? What does it look like? How large is it? And what is happening inside it? These are not rhetorical questions. Astronomers have been mapping the distribution of galaxies across the observable universe for decades, and what that mapping has revealed is not a featureless void, but a void with shape, an emptiness with architecture, and the architecture of that emptiness, the specific way in which the nothingness of the universe is organized, leads to something that is genuinely difficult to absorb without a long pause. As surveys of the universe have become more sophisticated, as instruments have grown more sensitive and observing programs have grown more ambitious, the large-scale structure of the cosmos has slowly come into focus. And what has emerged from that focus is a picture that, once seen, cannot be unseen. The galaxies of the universe are not distributed uniformly. They are not scattered randomly. They are organized into an enormous three-dimensional network of structures. Long filaments of galaxy clusters stretching across hundreds of millions of light years, wide flat sheets of galaxies called walls, dense knots at the intersections of filaments where thousands of galaxies pile together into massive clusters, and between all of these structures, enormous regions of relative emptiness, regions where the galaxy count drops to near zero, regions so large and so barren that standing inside one, if you somehow could, you might look in every direction and see almost nothing at the distance scales that, elsewhere in the universe, would be crowded with galaxies. These regions are called voids, not a romantic or dramatic name perhaps, but the word is accurate. Cosmological voids are, in the simplest terms, regions of the universe where the density of matter is far below the cosmic average. They are not absolute vacuums. There are still some galaxies inside them wandering lonely through their low-density interiors, but they are so much emptier than the surrounding cosmic web that they function, in the large-scale architecture of the cosmos, as gaps, as the spaces between the structure, as the dark ocean between the illuminated filaments and walls. And here is what makes voids more than just empty space. They are not passive. They are not simply where matter is not. They are the shapes that reality took because of how matter moved, how gravity worked, how the universe distributed its energies in the billions of years since it began. Understanding why voids exist and why they exist at the scales they do requires going back to the beginning of structure itself, back to a time when the universe was nearly uniform, when the differences between its densest regions and its emptiest were almost imperceptibly small, and when everything that the cosmos would eventually become was encoded in fluctuations smaller than the eye could ever see. But that explanation is not where the story ends. It is where it deepens. Because the voids are not simply historical artifacts. They are active features of the present universe, and there is something happening inside them, something connected to the most mysterious and poorly understood substance in all of physics, that suggests the emptiness of the cosmos is not merely where matter failed to gather, it is where something else entirely has taken hold, something that does not show up in telescopes, something that cannot be seen or touched or measured directly, something whose presence can only be inferred from the way everything around it behaves. And this something is quietly reshaping the future of every galaxy, every star, and every atom in the universe. The investigation, in other words, has only just begun, and every step forward into the emptiness leads not to clarity, but to a deeper absence, not to answers, but to a silence that, the longer you listen to it, becomes louder than anything you have ever heard before. To understand why the universe looks the way it does, why matter gathered into filaments and walls while enormous regions were left nearly empty, you have to go back to a time before any of the structure existed, not to the beginning of the universe exactly, but to a moment roughly 400,000 years after the Big Bang, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was a plasma, a hot, dense, opaque soup of charged particles so tightly coupled to light that nothing could travel freely. Photons bounced endlessly between electrons, unable to escape, carrying information about local densities but never releasing it. The universe was, in a meaningful sense, locked. When that lock broke, when the plasma cooled enough to become transparent and the light finally streamed free, what it left behind was a nearly uniform gas of hydrogen and helium spread across the entire observable volume of the cosmos. Nearly uniform, but not perfectly uniform. Encoded in that gas, imprinted in the temperature of the light that streamed away from it, were tiny fluctuations, regions that were fractionally denser than average, regions that were fractionally less dense. The differences were extraordinarily small, variations of roughly 1 part in 100,000 in the density of matter across the primordial gas. By any human standard, the universe at that moment was almost perfectly smooth, almost perfectly homogeneous, almost perfectly without structure. But gravity does not care about almost. Gravity is patient. It does not need the differences to be large. It only needs them to exist. And over the billions of years that followed, those tiny density fluctuations became the seeds of everything you see when you look at the cosmos today. The regions that were slightly denser than average began to attract more matter. Their gravitational pull, small at first but growing as more matter accumulated, drew in material from the surrounding space, and the regions that were slightly less dense than average began to lose material. Matter drifted away from them, pulled toward the denser regions, leaving the underdense zones progressively emptier. This process, sometimes described in the language of gravitational instability, operated simultaneously across the entire observable universe for billions of years. It was not a single event. It was a continuous, slow, relentless redistribution. Matter flowed from low-density regions toward high-density regions. Filaments formed where matter fell together along particular geometric alignments. Clusters formed at the intersections of filaments. Walls formed along planes where material from two opposing voids was squeezed together by converging flows of matter. And voids, those enormous empty regions, formed where matter had drained away in so many directions that almost nothing remained. What this means is that the cosmic web, the structure of filaments, walls, clusters, and voids that defines the architecture of the observable universe, is not simply a pattern in space. It is a record of time, a fossil of the gravitational history of the cosmos. Every filament encodes the direction in which matter preferred to flow. Every cluster marks a gravitational node around which material has accumulated across billions of years. And every void marks a region that gravity progressively abandoned, from which matter was drawn away toward the surrounding structure, until the void was left to itself, nearly empty, growing larger as matter continued to drain from its edges. The voids, then, are not accidents. They are the inevitable outcome of gravity operating on a universe that began with small, but non-zero fluctuations. They are the negative space of structure, the regions that had to empty so that the filaments and clusters could fill. In that sense, every great void in the cosmos is a kind of shadow, cast by the concentrations of matter that formed around it. And as with shadows, the larger the structure, the larger and darker the shadow it casts. Some of these voids are enormous by any measure you care to apply. There is a region of space in the direction of the constellation Bootes that astronomers have studied for decades, and that remains one of the most striking examples of large-scale emptiness in the observable universe. The Bootes void spans a region of space roughly 300 million light-years across. To put that number in perspective, the entire Milky Way galaxy is about 100,000 light-years in diameter. The local group, containing all of the galaxies gravitationally bound to our own, extends across perhaps 10 million light-years. The Bootes void is approximately 30 times larger than that. It is a region of space so enormous that if you placed our entire local group inside it, it would be a speck. And that speck would look out in every direction and find almost nothing. No clusters, no filaments, no walls of galaxies, for distances that would take light hundreds of millions of years to cross. When this void was first identified in the late 20th century, some astronomers were genuinely unsettled by it, not in the performative sense that science communication sometimes implies, but in a more technical and serious sense. The void was larger than their models of structure formation predicted. A single void should be able to grow in the time the universe had existed. It raised questions about whether the standard picture of how structure forms was complete. Those questions have since been substantially addressed. The Bootes void, while extraordinary, can be accommodated within modern cosmological models, particularly when the role of dark matter is properly accounted for. But its sheer scale remains something that takes genuine mental effort to internalize. You would not, standing inside the Bootes void on some imaginary observation platform, be surrounded by absolute darkness. The void is not empty in the way that a perfect vacuum is empty. There are some galaxies inside it, isolated, scattered, wandering through the interior of the void in small numbers. But the contrast between the void's interior and the walls and filaments that surround it is so dramatic that the interior feels, in any meaningful sense, abandoned. If you could observe from within it, you might look toward the edges and see a distant brightening, a distant wall of clustered galaxies. But in the interior direction you would see almost nothing at the scales that should be teeming with structure. It would be in a way that no isolated location on Earth or in the solar system can fully approximate, genuinely, profoundly alone. But it goes deeper. The Bootes void is one example, but it is not unique. The observable universe contains many voids, hundreds of them catalogued, ranging in size from tens to hundreds of millions of light-years across. When you map the full three-dimensional distribution of galaxies out to the distances modern surveys can reach, what you see is not a smooth distribution punctuated by occasional gaps. What you see is a structure that is predominantly void. The filaments and walls, for all their visual drama when rendered in maps, occupy a minority of the total volume. The voids, the empty regions, the spaces between the structure, account for something closer to 80 or 90% of the total volume of the observable universe. This is the number that should stop you, not 80 or 90% of the mass, not 80 or 90% of the energy, 80 or 90% of the volume, of the actual physical space that the observable universe occupies. The great majority of that space contains almost nothing. No galaxies, no clusters, no filaments, just the faintest trace of matter and the deep, unbroken quiet of a region from which the universe has effectively withdrawn. The cosmic web is real, and it is genuinely spectacular, but it is spectacular the way a spider's web is spectacular, not because of the solid threads, but because of how much open space they enclose, and how impossibly thin and fragile the threads appear against the emptiness they outline. Now consider what happens inside a void as time goes on. A void is not in equilibrium. It is not simply sitting at a low density while the rest of the universe continues to evolve around it. A void is actively evolving, and the direction of that evolution is, without exception, toward greater emptiness. As the matter on the edges of a void continues to be pulled into the surrounding filaments and clusters, the void's boundaries expand. The void grows. Matter drains from its periphery into the attractors outside, and the region of low density becomes larger and lower density still. Voids, over cosmic time, do not fill. They deepen. This is not merely a consequence of local gravitational dynamics. It connects to something operating at a far larger scale, something that has nothing to do with the matter in the filaments or the gravity of the clusters, something that is woven into the fabric of space itself, and that operates everywhere, at all scales, at all times, pushing every region of the universe away from every other region, something whose discovery, in the late 1990s, was one of the most disorienting moments in the history of cosmology. But the path toward that discovery begins in the structure of the cosmic web itself, in the way the voids relate to the filaments, and in what the geometry of that relationship implies about forces that were not originally part of the picture. To see why, it helps to think carefully about gravity. Gravity is an attractive force. It pulls matter together. Given enough time and enough matter, gravity will draw clouds of gas into stars, draw stars into galaxies, draw galaxies into clusters, and draw clusters into superclusters. This is the direction gravity always moves, toward aggregation, toward concentration, toward the gathering of matter into ever larger structures. Left to its own devices, gravity would eventually pull everything together, not necessarily into a single point. The universe is too large and expanding too fast for that to occur in any straightforward way. But gravity, if it were the only force operating on the large scale, would work against expansion, would slow down the separation of distant regions, would eventually perhaps halt the expansion entirely and draw the cosmos back on itself. The reason that is not what we observe is the reason the voids are growing. It is the reason the cosmic web is not simply a static structure, but an evolving one. It is the reason that distant galaxies are not slowly drifting apart under gravity's long reach, but are instead accelerating away from each other. And it is the reason that the emptiness of the universe is not merely a relic of the past, but an active and growing feature of the present cosmos. But the full explanation of what is driving that acceleration belongs to a slightly later part of this investigation. For now, stay with the structure, stay with the web, because there is something else about the cosmic web that deserves attention before we turn to the forces that are stretching it, something about its composition, about what it is actually made of. That is perhaps the single most disturbing revelation in all of modern cosmology. When you look at the cosmic web in maps produced from galaxy surveys, what you are seeing is light. You are seeing the light emitted by ordinary matter, by stars, by glowing gas, by the stellar populations of hundreds of millions of galaxies mapped across hundreds of millions of light years. And it is tempting to assume that what you are seeing, when you look at those maps, is the substance of the cosmic web. That the filaments are made of galaxies, that the clusters are made of galaxies, that ordinary matter, atoms, molecules, the stuff that stars and planets and living things are made of, is the primary ingredient of the universe's large-scale structure. It is not even close. The filaments are not made of galaxies. The galaxies are tracing the filaments. They are like foam on the surface of a wave. They reveal the shape of something much larger and more massive beneath them, but they are not the thing itself. The actual substance of the cosmic web, the material that provides most of the gravitational influence that organizes filaments, clusters, and walls, and that makes the voids the shapes that they are, is something that does not emit light, does not absorb light, does not interact with electromagnetic radiation of any kind. It cannot be seen, it cannot be imaged, it cannot be detected by any telescope ever built. It has been named, somewhat inadequately, dark matter, and its presence throughout the cosmic web is not a minor correction to the picture. It is the dominant ingredient. The evidence for dark matter does not come from a single observation or a single kind of measurement. It comes from many independent lines of evidence that converge on the same conclusion. There is far more mass in the universe than can be accounted for by everything we can see. The rotational speeds of galaxies imply the presence of far more mass than their visible stars and gas can provide. The gravitational lensing of light around galaxy clusters reveals mass concentrations far larger than any visible component can explain. The temperature distribution of hot gas in clusters, the large-scale distribution of galaxies in surveys, the specific pattern of temperature fluctuations in the cosmic microwave background, all of these, independently, point to the same thing. The universe contains a form of matter that interacts gravitationally but not electromagnetically, a form of matter that has mass and therefore gravity, but produces no light and leaves no electromagnetic trace, a form of matter that is, by its very nature, invisible to every instrument that relies on detecting photons. And this dark matter is not a minor constituent of the cosmos. It is not a small correction to the mass budget. Ordinary matter, every atom of hydrogen, helium, carbon, oxygen, iron, every element in the periodic table, everything that stars are made of and planets are made of and life is made of, constitutes roughly 5% of the total energy content of the universe. 5%. Dark matter constitutes approximately 27%. And the remaining 68%, the largest single component of the universe's total energy content, is something else entirely, something even more poorly understood, something that operates not as a substance at all but as a property of space itself. But set that aside for a moment. Stay with dark matter, 27% of the universe's energy content, gravitationally active, structurally dominant, and completely invisible. Dark matter is not distributed the way ordinary matter is. It does not cluster into compact objects the way gas collapses into stars. It forms diffuse, extended halos, enormous invisible clouds of gravitational influence that surround galaxies, that fill clusters, that thread through filaments, that exist everywhere that ordinary matter exists and in many places where ordinary matter does not. The cosmic web you see in galaxy maps is, in a very real sense, a map of the surface of dark matter structures. The galaxies formed where dark matter concentrated. The filaments of galaxies trace dark matter filaments. The clusters of galaxies sit inside enormous dark matter halos. And the voids, those enormous empty regions, are also, in the dark matter picture, regions of low dark matter density, regions from which even the invisible scaffolding of the cosmos is mostly absent. This means that the emptiness of the voids is even more complete than it appears. It is not just that visible matter is absent from the voids. The underlying structural substrate, the dark matter framework that, elsewhere in the universe, provides the gravitational backbone of all large-scale structure, is itself thinly distributed in voids. The voids are not simply gaps in the galaxy distribution. They are gaps in the dark matter distribution as well. They are regions where the universe's most abundant form of matter has itself been largely withdrawn, pulled toward the surrounding walls and filaments by the same gravitational dynamics that created the cosmic web in the first place. And this leads to something more disturbing. If you were to ask what precisely fills the interior of a cosmic void, if you were to conduct an inventory of everything present inside a region 300 million light-years across, the answer would be almost nothing. A handful of stray galaxies, each separated from the others by tens of millions of light-years, thin wisps of gas far too dispersed to ever collapse into anything. A faint, nearly undetectable background of dark matter, orders of magnitude less concentrated than in the surrounding filaments, and then, woven through all of it, interacting with none of it through any force other than gravity, pervading every cubic meter of space in the void just as it pervades every cubic meter of space in the densest cluster, the third component, the one that is not a substance at all, the one that is, in some sense, the most disturbing element of the entire picture. But before that, before the explanation of what fills the voids most completely, it is worth pausing on what the voids represent within the cosmic web, and why their existence matters to the story of the universe's future. The cosmic web is often described as the largest structure in the universe. This is accurate in the sense that it is the largest organized, coherent pattern that matter has formed. But this description can be subtly misleading, because it implies that the cosmic web is a stable structure, that the filaments, the clusters, the walls, the voids, are features of the universe that will persist more or less as they are, changing slowly, but not fundamentally, for the foreseeable future. This is not what the physics implies. The cosmic web is not in equilibrium. It is not a stable pattern. It is a snapshot of a structure that is actively evolving, and the direction of that evolution is, in important ways, toward dissolution rather than toward elaboration. Some parts of the web will grow denser over time. Clusters will continue to grow, absorbing smaller groups and filaments that fall within their gravitational reach. The largest gravitational attractors in the observable universe will continue to pull in matter from the surrounding regions, building ever more massive structures at the nodes of the web. But the web itself, the global pattern, the vast three-dimensional architecture of filaments and walls and voids, is under pressure from the expansion of the universe in a way that will, over sufficiently long timescales, make the web as a whole unrecognizable compared to what it looks like today. The reason for this lies in the expansion itself, and in what drives it, and to understand that, you need to grapple with the 68%. For most of the 20th century, the standard expectation in cosmology was that the universe was expanding, but that its expansion was slowing down. This made intuitive sense. The Big Bang had given everything in the universe an initial outward momentum. Every region of space was moving away from every other region, carried by the expansion of space itself. But gravity, operating between all the matter in the universe, should have been decelerating that expansion, pulling back gradually on the outward motion. The question cosmologists asked was not whether the expansion was decelerating, but by how much, and whether it would eventually halt and reverse. The answer that arrived in the late 1990s was not a more precise measurement of the deceleration. It was the discovery that there was no deceleration. The expansion of the universe was not slowing down. It was speeding up. Galaxies that should have been slightly closer to us than the naively calculated expansion predicted, because gravity should have slowed the expansion slightly in the time their light took to reach us, were instead slightly farther away. The universe was not decelerating under the pull of gravity. It was accelerating, driven by something that was not only counteracting gravity at large scales, but overwhelming it. That something became known as dark energy. The name is a placeholder for ignorance. It describes an observation, not a mechanism. What is known about dark energy can be summarized in a few empirical statements. It permeates all of space. Its density remains constant as the universe expands. Unlike matter, which becomes more dilute as space grows, dark energy maintains the same energy density per unit volume regardless of how large the volume becomes. It exerts a kind of repulsive effect at the largest scales, causing regions of space to accelerate away from each other, and it constitutes approximately 68% of the total energy content of the universe. The implications of these properties are profound and, the longer you sit with them, increasingly unsettling. Dark energy is not a force in the conventional sense. It does not push galaxies. It does not act on matter directly. What it does is drive the expansion of space itself, and it does this uniformly everywhere at all times. Every cubic meter of space has the same dark energy density. As the universe expands and more cubic meters of space come into existence, the total amount of dark energy increases, which means its repulsive effect on the expansion also increases. The more the universe expands, the more dark energy there is to drive further expansion. The process is self-reinforcing, and it is not reaching a limit. It is accelerating. This is what the voids are expanding into, not into pre-existing empty space. Space does not work that way. The voids are growing because the space within them is expanding, carrying their boundaries outward, pushing their edges further from their centers, increasing the volume of their interiors. And since dark energy's density does not dilute with expansion, the voids are not simply getting bigger. The rate at which they are getting bigger is itself increasing. The voids are accelerating their expansion, just as the universe as a whole is accelerating its expansion. And the matter on the edges of the voids, the galaxies and clusters that define the boundaries of the filaments and walls, is being carried along by this expansion, slowly, steadily, toward a future in which the distances between structures are larger than they are today by factors that are difficult to contemplate. Consider what this means for the cosmic web as a whole. On small scales, within clusters and superclusters, gravity is strong enough to hold structures together against the expansion of space. The Milky Way and Andromeda, for example, are gravitationally bound and are in fact approaching each other, destined to merge in a few billion years despite the expansion of the universe. The local group is gravitationally bound, and will remain so. The Virgo supercluster has gravitational coherence that can, in part, resist the expansion, but beyond a certain scale, beyond the reach of gravity in any bound or nearly bound system, the expansion of space dominates. And on those scales, the expansion is not just moving things apart, it is accelerating the separation. It is widening every void. It is stretching every filament. It is increasing every intergalactic distance in a way that, over long enough timescales, will have consequences that are genuinely, measurably catastrophic for the large-scale structure of the universe. The galaxies that are today visible at the edges of the observable universe, the ones whose light has taken nearly 14 billion years to reach us, are already, right now, so far away that the space between us and them is expanding faster than the speed of light. This does not violate relativity because it is not the galaxies moving through space at superluminal speed. It is the space between us and them expanding, adding distance faster than light can cross it. Any light those galaxies emit right now will never reach us. It will be carried away from us by the expansion of space faster than it can travel toward us. Those galaxies are already beyond our causal horizon. They have already, in the most complete sense, left our universe. And that horizon is not a fixed boundary. It is a moving one. As the expansion of space accelerates, more and more of the currently observable universe will be swept beyond that horizon. Galaxies that are today visible, today measurable, today providing information about the nature and history of the cosmos, will one by one cross that boundary and vanish. Their light will stretch to wavelengths too long to detect. The expansion will redshift that light beyond any conceivable instrument's ability to measure. And then effectively, those galaxies will cease to exist for any observer within our causal bubble. They will not have been destroyed. They will simply have been carried beyond reach, irretrievably separated from us not by any violent event, but by the quiet, steady, accelerating expansion of the space between. This is what the voids are growing toward. This is the direction in which the large-scale structure of the universe is evolving. Not toward greater complexity, not toward greater connectivity, not toward a fuller and richer cosmic web, but toward greater isolation, greater separation, greater emptiness. The voids will grow until the structures that once bounded them have been carried so far apart that the concept of a cosmic web loses meaning, until the filaments are stretched so thin that they no longer connect anything to anything, until each gravitationally bound system, each cluster or group of galaxies, is surrounded by a void so vast, so deep, and so rapidly expanding that nothing beyond it can ever be seen or reached or known. The universe is not static. It is not simply large. It is becoming larger, and the rate at which it becomes larger is increasing, and the consequence of that accelerating enlargement is a cosmos that is, with every passing billion years, more isolated, more fragmented, more empty. The cosmic web, this extraordinary, intricate, beautiful structure that took billions of years of gravitational evolution to create, is being unwound by an expansion that does not stop, that does not slow, that does not respond to gravity at the largest scales the way gravity responds to itself at smaller ones. The web is transient. What comes after it is not something else. What comes after it is the void. But to fully understand the depth of that future, to understand what the combination of dark matter, dark energy, accelerating expansion, and the architecture of the cosmic web implies for the long-term destiny of the universe, you need to sit with the expansion itself for a while longer. You need to understand not just that distant galaxies are moving away, but how that motion relates to what any future observer will be able to see. Because the story of expansion is also ultimately a story about information, about what can be known and what cannot, about the universe gradually hiding itself from itself. And that story begins with the light that is already on its way to somewhere, and whether it will ever arrive. Light is the only messenger the universe has ever sent us. Every piece of information we possess about anything beyond the Earth, every measurement of a star's temperature, every calculation of a galaxy's distance, every map of the cosmic web, every detection of the afterglow of the Big Bang itself, arrived in the form of photons. Particles of light traveling across space at the maximum speed the universe permits, carrying within their wavelengths and intensities a compressed record of where they came from and what they passed through on their way to us. The entire edifice of modern cosmology rests on the assumption that light is a reliable and sufficiently comprehensive messenger, and for the most part, within our current observational reach, it is. But light has a problem. It is fast, but space is expanding. And when space expands fast enough, light cannot cross it. This is not a technological limitation. It is not a constraint that a better telescope or a more sensitive detector could overcome. It is a fundamental feature of the relationship between the speed of light and the expansion rate of the universe. When the expansion of space between a source and an observer proceeds faster than the speed at which light travels, the light emitted by that source will never reach the observer. The photons will travel faithfully at the speed of light, but the space they are trying to cross will be growing faster than they can traverse it, and they will spend eternity receding from their destination. They are not slow. The universe is simply too large and getting larger too quickly for them to succeed. This creates what cosmologists call a cosmic horizon. Not a horizon in the sense of a physical boundary or a wall. There is nothing there, no edge, no surface, no structure of any kind. The cosmic horizon is a distance in every direction from any given observer, beyond which light emitted right now will never arrive at that observer's location. It is a sphere of reachability. Inside it, communication is in principle possible. Outside it, nothing that happens can ever affect you, and nothing you do can ever affect it. The cosmos beyond the horizon is not simply far away. It is causally disconnected. It is a universe that, for all practical and theoretical purposes, does not exist for you. What makes this cosmologically significant, what makes it more than an interesting mathematical curiosity, is that this horizon is not fixed. As the expansion of the universe accelerates, the rate at which distant regions are being carried away from us increases. And as that rate increases, the distance at which the expansion speed exceeds the speed of light decreases. The horizon is slowly contracting, in the sense that the volume of the universe that is in principle accessible to us, the volume from which we could, if we waited long enough, receive signals, is not growing. Given an accelerating expansion driven by dark energy, the volume of space from which future light can ever reach us is actually finite, and, over extremely long timescales, the number of galaxies within it is shrinking. Let that land for a moment. The universe is not simply becoming more distant, It is becoming smaller in the only sense that matters to any observer within it, the sense of what can be seen, known, and reached. The galaxies that exist beyond our current cosmic horizon are not merely far away, they are permanently beyond reach. And the galaxies that currently sit near the edge of our observable universe, those whose light has taken nearly the full age of the universe to reach us, are themselves moving toward that boundary of permanent disconnection. Not quickly, not dramatically. The process unfolds over billions of years, but it is a process with a clear direction, and the direction is toward less information, less connectivity, less universe. It gets worse. Because the cosmic horizon is not the only way in which the accelerating expansion erases information, there is also the question of redshift. As space expands, the wavelengths of photons traveling through it are stretched. A photon that begins its journey as visible light, emitted from a galaxy a few billion light-years away, will arrive at a detector somewhat redshifted, its wavelength lengthened, its energy reduced, because the space it traveled through expanded during the journey. The farther the source, the longer the journey, the more the photon is redshifted. Galaxies at the edge of the current observable universe are so strongly redshifted that the light they emitted in visible wavelengths arrives at us as radio waves. Only with radio telescopes can we detect it. Now imagine this process continuing for billions or trillions of years, as dark energy drives the universe's expansion to accelerate further, and as galaxies move progressively farther away, the light from even relatively nearby extragalactic sources will become more and more redshifted. Their light will stretch to longer and longer wavelengths. Their signals will grow fainter and fainter, not because the galaxies have become intrinsically dimmer, but because the photons carrying their light have been stretched to wavelengths so long they carry almost no energy. Eventually, the light from sufficiently distant galaxies will be redshifted beyond any physically meaningful limit of detection, stretched to wavelengths longer than the observable universe, carrying energies so small they cannot be distinguished from the quantum noise of empty space. Those galaxies will have gone dark, not because they burned out, but because the universe swallowed their signals on the way. And this leads to something more disturbing. Because some of the information being erased by this process is not merely the light from individual galaxies, it is evidence of the cosmos's history, evidence of the Big Bang itself, evidence of the large-scale structure that took billions of years to form. Consider the cosmic microwave background, the afterglow of the Big Bang, the ancient light that was released when the universe first became transparent, that has been traveling through space ever since, and that today arrives at Earth as a nearly uniform bath of microwave radiation coming from every direction. This radiation is among the most precisely studied phenomena in all of physics. Its temperature fluctuations encode information about the conditions of the early universe, about the distribution of matter before structure formed, about the seeds of the cosmic web itself. That radiation is already redshifted to microwave wavelengths from the visible light wavelengths it had when it was first emitted. It has been traveling for roughly 13.8 billion years and has been stretched by the expansion of the universe during that entire journey. But it is still detectable, still measurable, still encoding its ancient information in a form that contemporary instruments can read. Future observers, however, observers existing trillions of years from now, within a universe that has continued to expand under the influence of dark energy, will find that the cosmic microwave background has been redshifted far beyond microwave wavelengths. Its photons will have been stretched to such enormous wavelengths that their individual energies approach zero. The background will have effectively vanished, blending into the irreducible quantum noise of space. Its information will be gone, not destroyed in any dramatic sense, simply rendered inaccessible by the mathematics of expansion. A civilization existing in the deep future, long after the cosmic microwave background has faded below any detection threshold, would have no direct evidence that a Big Bang occurred. They would look at their universe and find no relic of that first flash of energy, no fossil light from the creation of the cosmos. They would have to reconstruct the history of the universe from first principles, from the compositions of stars, from the abundances of elements, from the physics of what they could see nearby, without access to the most fundamental cosmological dataset that we today take for granted. Their universe would not just look different from ours, it would be epistemically different, less knowable, stripped of historical testimony by the expansion of space. But in an important sense, that future civilization, if it existed at all, would be facing a problem far more severe than the loss of the cosmic microwave background. Because by the time the background has faded into noise, The structural context within which that civilization exists will also have changed almost beyond recognition. The galaxies that today define the observable universe, the hundreds of billions of galaxies spread across the cosmic web, will not all be gone, but most of them will be unreachable and invisible. Only the galaxies that are gravitationally bound to the local group, the ones close enough that their mutual gravity holds them together against the expansion, will remain within the observable horizon of any observer in that gravitationally bound system. Everything else will have been swept beyond the cosmic horizon. The rest of the universe and the vast majority of all the matter and structure that exists will have vanished from view, carried away by the silent, accelerating expansion of space. You might think that the remaining galaxies, crowded together within their gravitational bound system, would provide enough structure, enough material, enough light to sustain a recognizable universe. And in the short term, compared to cosmic timescales, perhaps they would. The merger of bound galaxies, which will happen over billions of years as gravitational dynamics drive them together, will create larger, more complex systems. The Milky Way and Andromeda will merge. The local group will eventually consolidate into a single large elliptical galaxy. Within that merged system, there will still be stars, still planets, still potentially the conditions for complex chemistry and whatever follows from it. There will still be light. For a very long time there will be light, but the context will have changed entirely. An observer in that merged galaxy, even one with the most sophisticated instruments imaginable, will look out at the sky and see essentially nothing beyond their own galaxy's stars. The surrounding universe will be dark, not dark as in a cloudy night, where the light is there, but obscured. Dark as in the light is not coming. Dark as in the sources of that light have been moved so far away that their photons can never reach this location. Dark as in the universe has contracted, observationally, to a single island of light in the middle of an infinite, expanding, unreachable void. This is the cosmological isolation that an accelerating universe eventually delivers. Not the destruction of what is local, not the annihilation of what is bound together by gravity, but the progressive, irreversible disappearance of everything that is not local. The universe does not end. It contracts. It contracts into observational islands, each one separated from all others by a growing void that no signal can cross, that no force can bridge, that no information can penetrate. The isolation is not metaphorical. It is physical. It is written into the equations that describe the relationship between dark energy, the expansion of space, and the propagation of light. There is a concept in cosmology called the Hubble volume, which refers to the spherical region of space around any observer within which the recession speed of matter is less than the speed of light. Outside the Hubble volume, space is expanding so fast that light cannot make progress toward the observer. The Hubble volume is not a fixed size. It depends on the expansion rate at any given time. In a universe with accelerating expansion, the Hubble volume reaches an eventual steady-state size determined by the dark energy density. Once the expansion rate has fully settled into its dark energy-dominated regime, the Hubble volume stops changing in size, and any galaxy that has not entered it and remained within it is gone, permanently, with no possibility of return. The number of galaxies within that eventual Hubble volume, in a dark energy-dominated universe, is a small fraction of the galaxies that exist today in the observable universe. Most of the current observable universe, most of the galaxies, most of the clusters, most of the filaments, most of the structure that makes the cosmic web what it is, will be beyond that boundary. It will exist, presumably, still evolving, still burning, still subject to its own local physics. But it will be forever unknown to anyone who is not inside it, and vice versa. The universe will have split into isolated cosmological bubbles, each one complete in itself, each one surrounded by an expanding void that no message, no probe, no force, no observation will ever cross. It gets worse, because even within those isolated cosmological bubbles, even within the gravitationally bound systems that will survive the expansion as coherent structures, the future is not one of stability. It is one of slow, inexorable transformation towards something that increasingly resembles the void that already surrounds them on all sides. To understand why, you have to follow the story of stars, because stars are the visible universe. Every photon that has ever been received by a human eye or a human instrument, every measurement of cosmic distance, every probe of cosmic structure, every indirect detection of dark matter and dark energy, all of it depended at some point on starlight. Stars are the lanterns of the cosmos. And the universe has a finite supply of lanterns. Stars form from gas. They require gas, specifically cold, dense molecular gas, to collapse under gravity and ignite fusion in their cores. The universe today still contains substantial reservoirs of gas, both in and between galaxies from which new stars can form. Star formation is still happening across the universe at a rate that has already been declining for the past several billion years, but that has not yet approached zero. The peak of cosmic star formation occurred roughly 10 billion years ago. Since then, the rate at which new stars are being born across the observable universe has been falling, not catastrophically, not suddenly, but continuously and measurably. The universe is slowly winding down its star-forming activity, like a factory that is still running but whose raw material supply is being consumed faster than it is being replenished. The gas supply is the key. Gas is consumed by star formation, converted into stars, locked into stellar interiors where it undergoes fusion, eventually expelled back into space in stellar winds and supernova explosions, but not always in a form that is easily recycled into new stars. Heavy elements produced by stellar fusion, carbon, oxygen, silicon, iron, do not as readily form new stars as the primordial hydrogen from which the first stars were made. The chemistry of star formation grows more complicated as generations of stars live and die, and the total amount of raw hydrogen available to form new stars is finite. It was fixed at the Big Bang, and it is being used up. The expansion of the universe makes this worse in a specific way. As dark energy drives galaxies beyond the cosmic horizon, the gas that might have been accreted from intergalactic filaments, the streams of gas that today still feed some galaxies and sustain some star formation, is cut off. A galaxy that is isolated within its gravitational bubble, surrounded by an expanding void, can no longer draw in fresh gas from outside. It must make do with what it has, and what it has is finite. Over time, that gas is consumed. Stars form from it, age, and die. The reservoir empties. Star formation slows, and eventually, over timescales of trillions of years, it stops. The universe will not, of course, go suddenly dark when star formation ends. The stars that exist at the time star formation ceases will continue to burn for varying lengths of time depending on their mass. Massive stars, the brilliant, hot, blue-white stars that produce most of the light in young galaxies, burn their fuel quickly. A star 10 times the mass of the Sun might live only 10 million years before exhausting its fuel and ending in a spectacular collapse. These stars are already gone from the early universe. The stars burning today in our galaxy and in galaxies throughout the observable universe are predominantly the smaller, cooler, more economical ones. And among these, the smallest and coolest, the red dwarf stars, are extraordinarily long-lived. A red dwarf star with a mass of roughly 1/10 the mass of the Sun burns its hydrogen so slowly and so efficiently that it can sustain fusion for trillions of years, timescales 100 to 1,000 times longer than the current age of the universe. The smallest red dwarfs may burn steadily for 5 to 10 trillion years. These stars are not dramatic. They produce a dim, reddish light, far less luminous than our own Sun. They are not the kind of stars around which complex photosynthesis is straightforward, but they are real. They are numerous. Red dwarfs are the most common type of star in the galaxy by a large margin, and they will be the last stars standing. Long after the Sun has exhausted its fuel and the blue giants have all collapsed and the mid-sized stars have all faded into their final remnants, the red dwarfs will still be burning, still feeding tiny amounts of dim light into the surrounding darkness, still in the most minimal sense keeping the lights on. But even for red dwarfs, there is an end. Slowly, steadily, over those vast trillions of years, each one will convert its hydrogen to helium. Unlike larger stars, red dwarfs do not have the convective structure that would allow them to dredge fresh hydrogen from their outer layers into their cores as the fuel in the core runs low. Or rather, some of them do have convective mixing, which actually extends their lifetimes, but eventually even that resource is exhausted. The hydrogen is used up. Fusion slows and stops. The star contracts. It does not explode as a supernova. It lacks the mass for that. It simply fades. It becomes a dense, cooling ball of carbon and helium, no longer burning, no longer producing new light, just radiating away the residual heat of its long life into the surrounding space until it too reaches the temperature of its environment, until it too goes cold. In the far future, in timescales that make the current age of the universe look like a single breath, the universe will be populated not by burning stars, but by their remnants, white dwarfs, The cooling cores of stars like the Sun, no longer fusing, slowly radiating their stored heat into the cold surrounding space. Neutron stars, the ultra-dense collapsed cores of massive stars that ended their lives in supernovae, spinning and cooling and fading over billions of years. And black holes, the endpoints of the most massive stellar collapses, objects so dense that space curves around them completely, objects from which not even light can escape, objects that will outlast every other stellar remnant in the universe by an almost incomprehensible margin of time. Black holes do not burn. They do not age in the conventional sense. They sit. They pull in anything that ventures close enough to their event horizons. They grow when there is material to accrete, and when there is not, they simply persist. In the far future, the supermassive black holes that sit at the centers of galaxies will have consumed whatever material remains in their vicinity. Star formation will have ceased. The surrounding stellar population will have aged into cold remnants, and the black holes, stripped of their accretion disks and their infalling material, will simply persist, immense, silent, invisible, and nearly eternal. Nearly, because there is a quantum mechanical process, described theoretically by Stephen Hawking in the 1970s, by which black holes do not quite persist forever. The precise details are subtle, and their full implications are still debated among physicists. But the core claim is this: the quantum vacuum near a black hole's event horizon is not completely empty. Quantum mechanical effects cause pairs of virtual particles to appear and separate near the horizon in such a way that the black hole slowly loses energy and mass over time. The black hole radiates, not light in the conventional sense, not photons emitted by hot plasma, but a slow, incredibly cold thermal emission arising from quantum effects at the horizon. This Hawking radiation is fantastically faint for any black hole of stellar or galactic mass. For a black hole the mass of the Sun, the Hawking temperature is so close to absolute zero that it is orders of magnitude colder than the current cosmic microwave background. Such a black hole would actually absorb more energy from the CMB than it loses through Hawking radiation. It would not begin to net evaporate until the universe had cooled far below the current CMB temperature, which means it would not begin to net evaporate for an extraordinarily long time, but eventually in timescales so enormous that the numbers involved require scientific notation to write in any compact form. Timescales of 10 to the power of 67 years for stellar mass black holes, and timescales of 10 to the power of 100 years or more for the supermassive black holes at galactic centers. Even black holes evaporate. They shrink gradually as Hawking radiation carries away their mass energy. They do not disappear suddenly. The evaporation rate is inversely related to mass. Smaller black holes radiate faster, so as a black hole loses mass it begins to evaporate more quickly, until in its final moments it releases a brief burst of radiation and vanishes entirely. What remains after a black hole has fully evaporated is, as far as physics currently understands, nothing. No remnant object, no solid residue, just a dispersed cloud of radiation expanding outward from where the black hole used to be. And then there is nothing left. No stars, no stellar remnants, no black holes. Only the radiation that their evaporation produced, an incredibly diffuse, incredibly cold, incredibly long wavelength bath of photons and particles spreading outward through a universe that is itself still expanding, still cooling, still growing emptier with every passing moment. The universe at this stage is not violent. It is not dramatic. It is silent, cold, enormously large, and almost perfectly empty. The photons produced by the last evaporating black holes spread through space in which there is nothing left to interact with, nothing left to absorb them, nothing left to be changed by their passage. They simply travel, endlessly, through a universe that has run out of structure, run out of complexity, run out of anything that could reasonably be called an event. This state, the final state of a universe dominated by dark energy, in which all matter has either been consumed by black holes, converted to radiation, or dispersed into fundamental particles too sparse to interact, is what physicists call heat death. The name is somewhat misleading. It is not hot, it is the opposite. It is a state of maximum entropy, in which the universe has reached its most disordered, most diffuse, most featureless configuration, a state in which there are no temperature gradients remaining, no hot regions and cold regions between which energy can flow and work can be done, a state in which every possible thermodynamic process has already run to completion, and the universe has settled into a final equilibrium that is, in the truest physical sense, completely inert. Heat death is not a prediction that all physicists accept with equal confidence. There are alternative scenarios, some involving quantum tunneling events that could create new regions of different vacuum states, some involving speculative physics beyond the current standard model that might alter the ultimate destiny of the universe. But within the framework of the physics we currently understand, heat death is the most rigorously supported endpoint for a universe with a positive cosmological constant, a universe in which dark energy is real and constant, which, as far as every measurement made to date can determine, is the universe we inhabit. What makes heat death genuinely difficult to sit with is not its violence. There is none. What makes it difficult is its completeness. It is not the end of the universe in the sense of destruction. The universe will still exist, in a sense. Space will still be there. The laws of physics will still be operative, but nothing will be happening. Nothing will be able to happen. Every gradient will be gone. Every source of energy will be exhausted. Every structure will have dissolved. The universe will have achieved a state of perfect, universal, irremediable sameness, a sameness that is indistinguishable, practically and perhaps philosophically, from nothing. The universe will have completed its long, slow transformation from the extraordinarily structured, energetic, complex state of the Big Bang, all that fire and light and rapidly expanding plasma, to a state of almost perfect emptiness, almost perfect silence, almost perfect uniformity. It will have, in the most fundamental thermodynamic sense, forgotten itself. And running beneath all of this, beneath the expansion of voids, the isolation of galaxies, the fading of stars, the evaporation of black holes, the approach of heat death, there is a concept that ties all of these processes together, a concept so fundamental that it is sometimes described as the one law of physics that gives time itself its direction. That concept is entropy. Entropy, at its most basic, is a measure of disorder. More precisely, it is a measure of the number of ways a system can be arranged at the microscopic level, while still appearing the same at the macroscopic level. A hot star is a low-entropy object, in the sense that its energy is concentrated, its matter is organized, its photons are coherently produced and carry useful energy. A diffuse cloud of cold photons spread evenly through space is a high-entropy state, in the sense that there are vastly more ways for photons to be spread evenly through a large volume than there are for them to be concentrated in a hot, dense object. The second law of thermodynamics states that entropy in a closed system never decreases. It always stays the same, or increases. The universe as a whole is, as far as we can tell, a closed system, and its entropy has been increasing since the Big Bang. What the increase of entropy means, in the context of cosmic evolution, is that the universe is always moving toward states that are more disordered, more diffuse, more uniform, and less capable of sustaining the kinds of energetic processes, fusion, chemistry, biological metabolism, that require energy gradients to operate. Every star that burns is consuming an energy gradient and producing entropy. Every supernova that explodes is converting the stored gravitational and nuclear energy of a massive star into an expanding cloud of hot gas, more entropy, more diffusion. Every photon that escapes a galaxy and travels through intergalactic space, eventually redshifting beyond detectability, is carrying entropy outward. The universe is burning through its low entropy inheritance from the Big Bang, and the rate at which it does so, while slowing as stars die and black holes take longer and longer to evaporate, never reverses. This is the arrow of time, the direction of time's passage, the reason the past feels different from the future, the reason causes precede effects, the reason things break but do not spontaneously reassemble, is fundamentally the direction of increasing entropy. And on the largest scale, the direction of entropy increase is clear, from the Big Bang's extraordinarily structured initial state, through the long middle epoch of stars and galaxies and cosmic web, toward the final state of maximum entropy, the heat death, the ultimate diffuse uniformity, the perfect emptiness that is the universe's final word. There is something in this trajectory that is worth sitting with, quietly, for a moment. The universe began in a state of extraordinary potential. The initial conditions of the Big Bang, whatever their ultimate origin, represented an enormously low entropy, enormously ordered starting point. Out of that starting point came everything: the hydrogen that condensed into the first stars, the heavier elements forged in those stars and scattered by their deaths, the galaxies that assembled from clouds of gas and dark matter, the planets that formed from the debris of stellar evolution. The chemistry that, on at least one of those planets, eventually produced organisms capable of looking at the night sky and feeling something, feeling the beauty of it, feeling the weight of it, asking what it means. All of that, the entire chain of complexity from the Big Bang to the first human eye that ever looked at a star and wondered, is a temporary arrangement of matter and energy in a universe that is, on the largest and longest view, moving inexorably toward a state in which none of it is possible. The complexity was always a detour, a transient elaboration within a system that was always, at the level of its most fundamental physics, headed somewhere else, headed toward the void. Not the void as a beginning, but the void as an end. Not the void that the universe was expanding away from in its first moments, but the void that it has been building toward, in the growth of cosmic voids, in the acceleration of expansion, in the slow fading of stars, in the quiet evaporation of black holes. Throughout its entire history, the night sky, seen from a dark field somewhere on Earth, still looks full of light, still pulls at something wordless in the person standing beneath it, still gives the impression of a cosmos overflowing with presence, with structure, with the feeling that out there, something vast and significant is happening. And in a sense, that impression is not entirely wrong. Something vast and significant is happening, but it has been happening for a long time, and it is not the kind of event that continues indefinitely. The stars are burning, the voids are growing, the expansion is accelerating, the galaxies are moving apart. The information encoded in the cosmic microwave background is stretching toward inaudibility. The raw material for new stars is slowly being consumed. The universe is doing what the laws of thermodynamics have always required it to do. It is moving toward equilibrium, toward sameness, toward the state in which nothing changes because nothing can. And yet the full weight of that conclusion does not arrive all at once. It accumulates. It builds through the details, through the specific mechanisms by which the universe implements its long journey toward emptiness, through the precise way in which each layer of the cosmic story connects to the next. Because understanding that the universe tends toward disorder is one thing. Understanding exactly how that tendency plays out, what it looks like at each stage, what the cosmos actually becomes as it ages, what the specific texture of its dying is something else entirely. And it is in those details that the story becomes most difficult to look at without feeling something shift in the way you understand your position in the cosmos. Start with the galaxies. Not the distant galaxies already being swept beyond cosmic horizons, but the galaxies that will remain within gravitationally bound systems, the ones that will survive the expansion as coherent structures, drawn together by their mutual gravity into merged systems that persist long after the surrounding universe has faded from view. These galaxies will continue to evolve. They will not simply sit unchanged within their isolated cosmological bubbles, burning steadily and maintaining their current character. They will be subject to the same gravitational dynamics that have always governed them: collisions, mergers, tidal disruptions, the slow drain of stellar evolution, but in a context that becomes progressively more constrained as the surrounding universe withdraws. The merger of the Milky Way and Andromeda, expected to begin in a few billion years and complete over the following billions of years, is not an unusual event. Galaxy mergers are common in the universe's history. They are, in fact, one of the primary mechanisms by which galaxies grow. Small galaxies fall into larger ones. Large galaxies collide and combine. The resulting system reorganizes itself gravitationally, often producing a large elliptical galaxy from what were previously two spiral galaxies, a puffed-out, roughly spherical cloud of stars with no clear disk structure, burning through its remaining gas more quickly as the merger triggers bursts of star formation. These starbursts consume gas reservoirs rapidly, accelerating the depletion of the material that new stars require. After the merger is complete, after the stars of both galaxies have been mixed into a single, slowly rotating cloud, the merged system will begin a long, slow process of stellar aging. The most massive stars will already be gone, having burned out during the merger and its associated starburst phase. Mid-sized stars will be aging toward their white dwarf endpoints. The small, long-lived red dwarfs will still be burning dim and steady, contributing the majority of the surviving star count while contributing a smaller fraction of the total luminosity. The galaxy, from the outside, will appear redder than it does today, cooler, less energetically violent, the blue light of massive young stars absent, the red light of aging smaller stars dominant. This reddening is not merely an aesthetic change, it is a symptom. It is what a galaxy looks like when it has consumed most of its star-forming potential and is living on what remains. Astronomers already see this process in the universe today. There are galaxies classified as red and dead, elliptical systems that exhausted their gas supply billions of years ago and have been aging in place ever since, their stellar populations cooling toward the long timescales of red dwarf evolution. These galaxies are not unusual or exotic. They are simply further along the path that all galaxies are eventually traveling. They are previews of what all gravitationally bound systems will eventually become. Within the merged local group system, this future Milkometa, as some astronomers informally call the merged Milky Way and Andromeda, the stellar population will slowly thin out over the following trillions of years, not because stars leave, but because they die and are not replaced. Each star that exhausts its fuel joins the growing population of remnants, white dwarfs cooling toward invisibility, neutron stars spinning down their rotational energy and fading, the occasional stellar mass black hole sitting silently at the end point of a massive star's life. The ratio of dark remnants to burning stars will shift steadily, over trillions of years, toward an increasingly remnant-dominated system. The galaxy will still exist in the sense that its stars and remnants will still be gravitationally organized in a coherent structure, but it will be progressively darker, progressively colder, progressively less capable of the energetic processes that define what galaxies are today. And even the structure of the galaxy itself is not guaranteed to persist unchanged over these timescales. On timescales of tens of trillions of years, timescales so large that our current universe's age fits within them more than 1,000 times, even the gravitational organization of a galaxy is subject to disruption. Stars interact gravitationally with each other even without direct collisions. In a system as dense as a galaxy, the cumulative effect of countless weak gravitational interactions between individual stars over vast timescales is not zero. It produces a slow diffusion of stellar orbits. Stars gradually exchange energy and angular momentum. Some stars are nudged into higher orbits, others are nudged inward. Over timescales of quadrillions of years, this process of gravitational relaxation has a specific outcome. A fraction of the stars in the galaxy gain enough energy from their interactions to escape the system entirely, gradually evaporating into the surrounding void, while the remaining stars sink inward and the core of the galaxy becomes progressively more compact, and the supermassive black hole at the center grows by consuming what falls into it. This process, galactic evaporation, is slow beyond any easy comprehension. It operates on timescales of 10 to the power of 19 or 20 years for a typical galaxy, numbers so large that the entire current age of the universe, at roughly 13.8 billion years, represents only a tiny fraction of the process's duration. But it is real. It is what gravity does to a self-gravitating system over sufficiently long timescales. The galaxy does not explode. It does not collapse all at once. It slowly loses its members to the void while its center becomes denser and denser. Stars escape. The galaxy shrinks. Eventually, what remains is not a galaxy in any recognizable sense, but a dense cluster of remnants around a growing black hole, surrounded by a vast, thinly spread halo of escaped stars, drifting through the expanding void. Those escaped stars, those isolated white dwarfs, neutron stars, and black holes drifting through intergalactic space, will themselves continue their slow cooling and fading. A white dwarf, cut off from any external energy source, will radiate its stored thermal energy into the surrounding space. The timescale for a white dwarf to cool to the temperature of the surrounding environment, to become in effect a cold, dark, crystallized ball of carbon and oxygen invisible against the background, is estimated at roughly 10 to the power of 15 years. At that point, the object is sometimes called a black dwarf, a cold, inert, dark, stellar remnant, no longer producing any detectable radiation, drifting silently through a universe that has no more use for it. Whether true black dwarfs actually exist in the universe is an interesting question. The current age of the universe is far too short for any white dwarf to have cooled to this endpoint. The oldest white dwarfs in the universe are still warm enough to emit faint ultraviolet and visible light. Black dwarfs, if the physics is correct, will not exist until the universe is many orders of magnitude older than it is today. They are a prediction of the far future, not an observation of the present, but they are a useful marker, a specific kind of object that represents one of the universe's final material states before even the cooling remnants of stars lose their last thermal energy to the surrounding void. And it gets worse, because protons, the fundamental building blocks of atomic nuclei, the particles at the heart of every atom of hydrogen, of every heavy element, of every white dwarf and neutron star and brown dwarf and cold rocky planet drifting through the expanding void, may not be stable forever. The stability of the proton is one of the more consequential open questions in particle physics. Certain theories that attempt to unify the fundamental forces of nature predict that protons are not truly stable, but instead decay over extraordinarily long timescales. Timescales on the order of 10 to the power of 34 years or longer, depending on the specific theoretical framework. Experimental searches for proton decay have so far found no evidence of it, which means that if protons do decay, they do so more slowly than the most sensitive current experiments can detect. But if protons are not stable, if they do eventually decay, transforming into lighter particles and radiation over some extraordinarily long timescale, then the ultimate fate of all ordinary matter in the universe takes a specific form. Every atom of every cold white dwarf, every black dwarf, every neutron star, every rogue planet drifting through intergalactic space will eventually disintegrate. Not explosively, not dramatically. One by one, proton by proton, over timescales that make the evaporation of stellar mass black holes look like a brief event, the ordinary matter of the universe will dissolve into lighter particles and radiation. The cold remnants of stars will lose their substance. The dark, drifting rocks that once were planets will break down into a warm, diffuse haze of particles. The very atoms that make up the ordinary matter component of the universe, that 5% of the total energy content that includes everything ever built, everything ever lived in, everything ever observed, will cease to exist as atoms. What remains after proton decay, if it occurs, is a universe that contains no ordinary matter at all, only the radiation produced by the decay, spreading outward through expanding space, and the black holes. The black holes, composed not of ordinary matter in the conventional sense but of warped spacetime from which ordinary matter has long since been absorbed and processed, persist. They do not decay through proton decay. Their fate is governed instead by Hawking radiation, and their timescales are, as described earlier, almost inconceivably long. The supermassive black holes, the ones billions of times the mass of the Sun sitting at the centers of what were once galaxies, will take something on the order of 10 to the power of 100 years to fully evaporate. 10 to the power of 100 years, a Google years. To get a sense of how large this number is, the current age of the universe is roughly 10 to the power of 10 years. A Google is 10 to the power of 100. The ratio of a Google to the current age of the universe is the same as the ratio of the current age of the universe to a time so short it would be meaningless to compare it to anything human. The number is not just large, it is in a category of largeness that renders ordinary intuitions about scale completely inapplicable, and yet it is a finite number. Eventually, even the last supermassive black hole will have shed all of its mass through Hawking radiation. It will emit its final brief burst of high-energy particles and radiation, and then it will be gone. After that, after the evaporation of the last black hole, what does the universe contain? A diffuse, extraordinarily cold, extraordinarily sparse bath of photons and fundamental particles. Photons from Hawking radiation, electrons, positrons, and neutrinos from various decay processes, all spreading through a space that is still expanding, that has been expanding continuously since the Big Bang, and that shows no sign, within any known physics, of ever stopping. The temperature of this bath will be fantastically close to absolute zero, closer than any temperature ever achieved in a human laboratory, closer than anything we have language to adequately describe, but not quite absolute zero, not yet, perhaps never, in any finite time. The particles in this bath are so sparsely distributed, separated by distances so enormous that the average separation between any two particles in the entire universe is measured in light years, or tens of light years or more, that interactions between them are vanishingly rare. Two electrons might pass close enough to interact once in a time span longer than the Google years it took for the last black hole to evaporate. The universe at this stage is not merely quiet, it is effectively static. Nothing is happening not because there is a law prohibiting it, but because the raw material for anything to happen, a temperature gradient, a chemical interaction, a gravitational attraction between concentrations of mass, has been entirely consumed by the long entropic journey to this point. This is the universe in its final, stable configuration, not a final state in the sense of a wall that the universe hits and stops. Space continues to expand, the photons continue to travel, the occasional quantum fluctuation presumably still occurs somewhere in the vastness, but nothing builds from those fluctuations. There is no longer enough energy concentrated anywhere to bootstrap any kind of structure, any kind of process, any kind of event that would be recognizable to a physicist as interesting. The universe has become, for all meaningful purposes, a perfect void. Not the void between the galaxies that we observe today. That void still contains photons, still contains the faint microwave background, still contains the quantum fields that permeate all of space and could, in principle, support some physical activity. This final void is deeper. It is the void that the universe spent its entire history constructing, one step at a time, by converting every source of usable energy into unusable, maximally distributed, maximally entropic radiation. What is perhaps most striking about this endpoint, what makes it genuinely difficult to hold in mind without a kind of vertiginous disorientation, is that it was, in some sense, always the destination, not in a teleological sense. Not as if the universe had a plan or a direction or an intention. The laws of thermodynamics do not have intentions, but the laws of thermodynamics do have a direction, and the direction they have always pointed is toward this: a universe in which all the remarkable, intricate, energetic, complex, beautiful arrangements of matter and light that we observe, all the stars and galaxies and cosmic webs and living things and the minds that those living things contain, were always temporary, were always the middle of the story, were always a phase in a longer process that began before stars and will end after them. The universe began in fire, in an extraordinarily hot, dense, energetic state in which space itself was expanding faster than light, in which temperatures were so high that matter and antimatter were continuously created and annihilated, in which the four fundamental forces of nature were possibly unified into a single interaction before symmetry-breaking events separated them into the distinct forces we know. From that fire came protons and neutrons. From protons and neutrons came hydrogen and helium. From hydrogen and helium drawn together by gravity and dark matter into the first structures of the cosmic web came the first stars. And from those stars, whose cores forged heavier elements under the crushing pressure of their own gravity, came the raw material for everything that followed: planets, chemistry, and ultimately the particular arrangement of carbon and water and chemistry that asked the first question about any of this. That question, what is all of this and where did it come from and what happens to it, is one of the most improbable things in the known universe. The conditions required to produce a mind capable of asking it are extraordinarily specific. They require a particular range of stellar evolution, a particular chemistry, a particular planetary environment, a particular length of time during which the conditions remain stable enough for biological complexity to develop. And all of those conditions are temporary. All of them depend on the universe being in a specific phase of its long history, the phase in which stars still burn, in which planets still orbit stable suns, in which the cosmic microwave background is still warm enough to be detectable, in which the galaxies are still close enough to be visible, in which the universe's low entropy inheritance from the Big Bang has not yet been fully spent. We are in that phase now. The universe is currently in the middle of its stellar era, the long epoch stretching from roughly 100 million years after the Big Bang to perhaps 100 trillion years into the future, during which stars burn and the cosmos is lit. We are not at the beginning of that era. The peak of cosmic star formation is already behind us by several billion years. We are in a universe that is, on the longest view, past its most energetically productive period and slowly winding toward the dimmer, cooler, emptier phases that come after. But we are nowhere near the end of the stellar era. Stars will burn for trillions of years yet. The universe is not dying quickly. It is dying slowly, in the way that all large, complex systems with finite energy supplies die slowly, through the gradual and irreversible conversion of usable energy into unusable energy, through the patient and indifferent operation of thermodynamic law. The indifference is perhaps the most important word. The universe does not choose its fate. It does not experience its own aging. It does not know that the voids are growing, that the galaxies are separating, that the stars are slowly exhausting their fuel, that the entropy of the system has been increasing since the moment of its creation, and shows no sign of any law or mechanism that could reverse the trend. The universe is not tragic in the way that a living thing experiences tragedy. It simply is, and it is what it is according to the physics that governs it, and the physics that governs it leads, without exception, to a future that is emptier and colder, and more uniform, and less capable of surprise than the present. The tragedy, if that word applies at all, belongs to the perspective. It belongs to the fact that the universe produced, in its middle age, arrangements of matter complex enough to observe themselves, complex enough to map the cosmic web, complex enough to detect the faint microwave remnant of the Big Bang, complex enough to infer the existence of dark matter, from the motions of galaxies, and dark energy, from the recession rates of supernovae, complex enough to project the universe's history forward through its long twilight and into the silence that follows. And having done all of that, having assembled that remarkable, improbable temporary instrument of self-observation, the universe does not reward the observation with comfort. It does not offer a reason. It does not suggest that the complexity was the point. It simply presents its physics, its timescales, its directions, its endpoints, and continues indifferently on its way. The night sky that seemed full of light at the beginning of this investigation has not changed. The stars are still there. The galaxies still glow. The photons from Andromeda are still arriving, still carrying their 2.5 million year message. But the frame has changed. What appeared to be a filled, rich, abundant cosmos, a universe overflowing with presence and structure, and the warm light of 100 billion galaxies, is now visible for what it actually is: a thin, temporary, locally concentrated arrangement of matter in a universe that is predominantly empty space, driven by forces that are mostly invisible, expanding under the influence of something that constitutes 2/3 of all the energy in existence and that cannot be seen or touched, heading toward a future in which the current arrangement is not maintained but dissolved. The voids will grow. They are growing now, measurably, in real time, as dark energy stretches the space within them and pulls their boundaries outward. The galaxies at the edges of those voids are receding from each other. The filaments of the cosmic web are being stretched. The clusters, bound by their own gravity, persist for now, but the universe surrounding them is becoming progressively emptier. The observable horizon contracts. The number of galaxies visible to any observer within the universe shrinks. The cosmic microwave background redshifts toward inaudibility. The star-forming rate falls. The stellar population ages. The universe cools. And here, at the end of this long descent through scales and timescales, through the architecture of emptiness and the mechanics of cosmic fate, one final image presents itself, not of violence, not of explosion or collapse, not of any dramatic terminal event, but of distance, of the final state of a universe that has spent its entire history separating itself from itself, moving matter into isolated islands, stretching the space between those islands, and then slowly, over unimaginable timescales, cooling those islands into silence, until what remains is a space so vast and so empty and so cold that the concept of distance loses its meaning. There is no here and there. There is no near and far. There is only the expanding void, the occasional photon completing its endless journey through a universe that has nothing left to offer it, and the deep, perfect, irremediable silence of a cosmos that has finally, after a duration that makes its entire luminous history look like a spark, come to rest. The universe did not begin in silence. It began in the most energetic event in the history of anything we can describe, but silence may be where it ends, not the comfortable silence of a room at night, where the quiet is temporary and surrounded by the possibility of sound. A silence more complete than that. A silence that is the natural consequence of thermodynamics, of dark energy, of the particular physical laws that govern this particular universe. A silence without audience, without witness, without even the possibility of being broken by anything, because there is nothing left that could break it. What you see when you look at the night sky tonight is a universe in the middle of that process, young enough that its stars still burn, that its galaxies are still visible, that the structure it built over its first billion years is still largely intact, but old enough, and expanding fast enough, and cooling steadily enough, that the direction is clear. What appeared full is mostly hollow. What appeared permanent is temporary. What appeared abundant is finite. And the finite is being spent, slowly and inexorably, in the direction of an emptiness so complete that it makes the voids we mapped at the beginning of this investigation, those enormous, 300 million light-year gaps in the cosmic web, look, by comparison, like almost nothing at all, because they were nothing at all. They were the preview, the universe's long practice at becoming what it was always, by the laws that govern it, going to become. There is no final message in any of this, no moral, no redemptive arc. The physics does not offer one. The thermodynamics does not offer one. The dark energy does not care. The voids do not listen. The expanding cosmos does not pause to acknowledge what it is doing or what it is leaving behind. It simply continues, expanding, cooling, emptying, as it has done since its first moment, as it will do after its last structure has dissolved, as it will do in the silence that follows, in a space so vast and so empty that the word vast no longer carries sufficient weight, and the word empty no longer captures the depth of what is there. This is the universe, not the one that appears when you look up at a clear night and feel something ancient and wordless stir in you. That universe is real, but it is the surface. Beneath the surface, in the structure of the cosmic web and the nature of dark matter and the behavior of dark energy and the mathematics of expansion and entropy and the long, cold future that those mathematics describe, is this other universe, the one that is mostly nothing, the one that is becoming more nothing with every passing moment, the one that will, in a time so distant it cannot be meaningfully named, be indistinguishable from the void it was born expanding into, the universe that was always, underneath the light, mostly silence, and that is, quietly and completely, becoming silence at last. But silence as a concept deserves more precision than we usually give it. When we call the final universe silent, we are not describing a subjective experience of quiet. We are describing a physical state in which the conditions necessary for any process, any interaction, any transformation, any event in the thermodynamic sense, have been exhausted. Silence, here, is not the absence of sound, it is the absence of change. And the absence of change is what maximum entropy actually means when you translate it out of the language of statistical mechanics and into the language of what exists and what happens and what is possible. This distinction matters because it clarifies something about the journey the universe is on. The universe is not moving toward silence in the way that a noisy room gradually quiets as people leave. It is not simply losing its most energetic components while a quieter substrate persists. It is moving toward a state in which the substrate itself, the thermodynamic capacity for anything to happen at all, is consumed. Every process that occurs in the universe, from the fusion of hydrogen in a stellar core to the collision of two galaxies to the formation of a single molecule of water on the surface of a rocky planet, draws on the universe's reserve of low entropy. Every process converts some of that reserve into high entropy, into heat, into diffuse radiation, into the maximally disordered configurations that thermodynamics always prefers. And that reserve, while enormous, is finite. It was endowed at the Big Bang and has been drawn down ever since. The Big Bang itself in this framing was not merely the beginning of the universe. It was the establishment of an extraordinarily low entropy initial condition, a state of such extraordinary order that everything which has happened since, every star that has burned, and every galaxy that has formed, and every complex structure that has assembled itself in the cosmic web, has been a consequence of the universe spending down that initial endowment. Not wastefully, not purposelessly, but inevitably, driven by the thermodynamic preference for disorder, for diffusion, for the maximally probable arrangement of energy and matter. The universe has been, since its first moment, a system burning through its inheritance, and the scale of that inheritance is genuinely extraordinary. The low entropy of the Big Bang was so extreme, the initial conditions so remarkably ordered compared to what could have been, that the universe has been burning through it for nearly 14 billion years and still has an immense amount remaining. The stellar era alone, the era of burning stars and lit galaxies, stretches for trillions of years ahead. The era of cooling white dwarfs and evaporating black holes extends for timescales, measured in googles of years. The universe's low entropy inheritance is not running out quickly. It is running out slowly, in a process so gradual that from within the brief window of the stellar era, it is almost impossible to feel the depletion happening. Almost, because there is one measurement that captures it, one observable quantity that, more than any other, reflects the universe's thermodynamic direction, the temperature of the cosmic microwave background. That temperature, currently approximately 2.7 degrees above absolute zero, is a direct measure of the universe's thermal state. It reflects the dilution of the Big Bang's original heat by the expansion of space over 13.8 billion years, and it is falling, slowly, imperceptibly from the perspective of any human lifetime, but falling nonetheless. As the universe continues to expand, the cosmic microwave background continues to cool. The photons that constitute it continue to redshift. Their average energy continues to decrease. The temperature continues to drop toward absolute zero. It will never quite reach absolute zero, at least not in any finite time, for reasons connected to quantum mechanics and the nature of the vacuum. But it approaches. It falls asymptotically, and as it falls, the thermal bath that permeates all of space becomes less and less capable of driving any thermodynamic process, less and less capable of supporting any chemistry, less and less capable of providing the energy differential that any physical event requires. The universe cools not just in the sense of becoming colder, but in the sense of becoming less available, less capable of being used, less capable of driving anything, less capable of the energetic generosity that, during the stellar era, it lavishes on every star it ignites. Consider what it means for a civilization, any civilization, anywhere in the universe, to exist within this thermodynamic context. Not our civilization, which exists in the cosmological present and has access to the full warmth of a middle-aged star and the full richness of the current stellar era, but a hypothetical civilization existing in the far future, within one of the isolated gravitationally bound systems that survive the expansion of the universe, surrounded by the expanding void and cut off from the rest of the cosmos. What does the universe look like to that civilization? What do they know? What can they discover? In the immediate term, within their own galaxy, within the merged and isolated system they inhabit, they might have access to considerable resources. Red dwarf stars still burning, the thermal energy of cooling white dwarfs, the gravitational potential energy of massive objects, the chemistry of planets orbiting long-lived stars. These resources are not trivial. They could, in principle, sustain complex physical processes and perhaps complex civilizations for timescales that dwarf anything in human history. A civilization that learned to harvest the dim but steady output of red dwarf stars could potentially persist for trillions of years, which is an almost meaninglessly long time by human standards. But the context of that civilization would be, in ways that matter deeply, profoundly impoverished compared to the context we inhabit now. They would look out at the sky and see their own galaxy's stars, dim, red, long-lived, aging, and beyond them, the void. No other galaxies visible, no cosmic web discernible, no cosmic microwave background detectable, no direct evidence of the Big Bang. They would be inhabitants of an island universe in the truest sense, a finite, isolated, self-contained system surrounded on all sides by an expanding emptiness from which no signal has ever arrived, and from which none ever will. Their cosmology, built from observations within that island, would be radically incomplete. They would have no way to know that the universe was once full of hundreds of billions of galaxies. They would have no way to measure the expansion of space with any of the tools that we use today, because the objects that anchor those measurements, the distant galaxies, the quasars, the supernovae and remote clusters, would all be gone from view. This is one of the more quietly disturbing implications of the accelerating expansion. The universe is not only becoming emptier, it is becoming less knowable. The information required to reconstruct the full history of the cosmos, the information encoded in the positions and velocities of distant galaxies, in the temperature fluctuations of the cosmic microwave background, in the distribution of matter across the large-scale structure of the cosmic web, is being progressively erased, not by any destructive process, but simply by expansion, by the stretching of space that carries information sources beyond the causal horizon and redshifts their signals into indetectability. The future universe is not just different from the present universe. It is a universe that contains less of its own history than the present universe does. A universe that has forgotten more of itself with each passing era, and this epistemic loss is permanent. There is no mechanism within known physics by which the information carried beyond the cosmic horizon can be recovered. Once a galaxy has been swept beyond the point where its light can reach us, it is gone from our causal universe as completely as if it had never existed. Not in physical reality, which we cannot access from here, but in the only sense that matters for any observer, the sense of what can be known. The universe does not keep records that outlast expansion. It does not archive its history in any retrievable form. The record of what the cosmos looked like in its full, structured, web-rich Middle Age is a record that will be available only to observers who exist during that Middle Age. After it, the record will be gone, irrecoverably, permanently, absolutely gone. It gets worse, because even within the stellar era, even now in the cosmological present before the distant future has had time to unfold, the universe is already implementing this erasure at the edges. The galaxies at the most distant reaches of our observable universe, those that formed in the first billion years after the Big Bang, are already receding from us faster than light. Their light, already ancient, was emitted when those galaxies were much closer than they are now, and reached us only because of the specific geometry of the expanding universe in its earlier, slower expanding phase. New light emitted by those galaxies today will never reach us. Those galaxies are already in real time beyond our causal horizon. They have already been lost. We are observing them in the past, catching the last light they will ever send us, and we will not know exactly when each one crossed the horizon because the crossing is not an event visible from here. It is a process defined entirely by the mathematics of expansion. What this means is that the observable universe, the sphere of space from which we can, in principle, receive information, is already a subset of the full universe, and it is a subset whose edges are already defined by the irreversibility of expansion. The full universe, whatever its actual extent, contains regions that have been causally disconnected from us since before we existed, regions that formed, evolved, and perhaps went through their entire stellar life cycles in complete causal isolation from our own, regions that we will never reach and whose existence we can only infer from the mathematics of the early universe's homogeneity. The full universe is, in a sense, already fragmented, already divided, already implementing the isolation that the far future will complete. The observable universe itself is often described as a sphere roughly 93 billion light-years in diameter, the region from which light has had time to reach us since the Big Bang, accounting for the expansion of space during the journey. This is a large number, a very large number, but it is a finite number. And within this finite sphere, the total amount of matter and energy and information is fixed, or rather, it is decreasing, as the horizon contracts under accelerating expansion, and regions that were once within it are carried beyond. The universe we can observe is shrinking, the universe we know is shrinking, and the universe we will ever be able to know is smaller than the universe we can observe today, because the light from some of those currently observable galaxies has already been the last light they will ever send us. There is something in this, in the image of a finite shrinking sphere of knowability surrounded by an infinite, inaccessible, eternally expanding void, that captures something essential about the universe's character. The cosmos is not a place that opens as you explore it. It is a place that closes. Every observation extends knowledge in one direction, while the accelerating expansion quietly closes doors in every other direction. We are in a race we cannot win, not because we lack the technology, but because the race itself is not a race between observers and distance. It is a race between the speed of light and the expansion of space. And the expansion of space, in a dark energy-dominated universe, has already won. It won billions of years ago, when the expansion rate crossed the threshold beyond which most of the universe's volume became permanently inaccessible. We have been living inside the consequences of that victory ever since, without, for most of human history, even knowing the race had taken place. But go back to the structure of the cosmic web for a moment, back to the voids and filaments and clusters that we mapped at the beginning of this investigation, and look at them again in light of everything that has been established since. The voids are growing. Their interior space is expanding under dark energy. Their boundaries are being pushed outward, as matter drains from their edges into the surrounding filaments, and as the space within them expands. The filaments themselves are being stretched by the expansion, thinning over time, becoming less connected as the distances between their component galaxies increase. The clusters, anchored by their own gravity, persist as coherent structures, but the space surrounding them grows emptier and more rapidly expanding with every passing epoch. The cosmic web, viewed on the timescale of the universe's future, is not a stable structure. It is a temporary pattern in a medium that is becoming uniformly smooth. The initial fluctuations that seeded the web, those 1 part in 100,000 density variations in the primordial gas, drove a process of structure formation that peaked billions of years ago and has been running on its momentum ever since. The great age of structure formation, when new clusters and filaments and walls were actively assembling from infalling matter, is largely behind us. The universe is now in a phase of structural maturation and, on the longest view, structural dissolution. The web formed, reached its peak complexity, and is now subject to the forces, expansion, dark energy, entropy, that will, over sufficient time, undo it. This is perhaps the most sobering way to understand the cosmic web, not as a permanent feature of the universe's architecture, but as a phase in its biography. A phase that from the inside, during the brief epoch of its full expression, looks like permanence, looks like structure, like organization, like the universe having settled into a kind of maturity, but is, on the longer view, a transient elaboration of matter, the most complex thing the universe has ever produced, unquestionably, that is subject to the same thermodynamic and cosmological forces that govern everything else. The web is temporary. Its voids will win in the end. Not because emptiness is stronger than structure in any active sense, but because the forces that built the structure, the initial low entropy of the Big Bang, the gravitational amplification of primordial density fluctuations, are finite, while the forces that are undoing it, dark energy, expansion, entropy, are not. And this leads to a final reflection on the nature of emptiness itself. Throughout this investigation, emptiness has been treated as the absence of something, as the space between the galaxies, as the void that opened when matter drained toward filaments and clusters, as the silence that the universe is moving toward as its energetic resources are spent. But there is another way to think about it. The emptiness of the universe is not merely the absence of matter. It is the dominant state of the cosmos. It is the condition that defines more of the universe's volume than anything else, that has characterized the cosmos throughout its history, and that will characterize it long after the last star has faded and the last black hole has evaporated. Emptiness is not a side effect of the universe. It is the universe's primary mode of existence. Matter, the stuff that stars and planets and galaxies are made of, the stuff that living things are made of, the stuff that produced the question of what the universe is the anomaly, the temporary, local, improbable exception. The entire observable universe, with all its hundreds of billions of galaxies, all its dark matter halos and cosmic filaments and gravitational clusters, all its burning stars and cooling remnants and black holes and planetary systems, all the complexity it has produced in 14 billion years of thermodynamic evolution, all of that is a thin, temporary, locally concentrated elaboration at the edge of an immensity of nothing. The nothing was there before the structure. The nothing will be there after the structure. The nothing surrounds the structure on every side and at every scale. And the nothing, the void, is not waiting. It is already here. It has always been here. The universe did not create structure from nothing and then maintain it. It created a brief, remarkable, thermodynamically expensive departure from nothing and has been returning to nothing ever since. This is what the voids reveal when you follow them far enough. Not just the architecture of the cosmic web, not just the distribution of dark matter, not just the influence of dark energy and the mathematics of expansion. They reveal the universe's direction, its tendency, its preference, encoded in the second law of thermodynamics, for the state that is most probable, most diffuse, most structureless. The voids are not aberrations in an otherwise structured cosmos. They are prefigurations of a cosmos that is, on its longest time scale, entirely void. The universe is not a place of things. It is a place of nothing, temporarily interrupted by things, and the interruption is ending. Slowly, quietly, on timescales that make the entirety of human history look like a mathematical rounding error, the interruption is ending. And what comes after it is not something. What comes after it is the completion of what the void has always been: vast, cold, expanding, silent, and perfectly, finally, empty. If you go outside tonight and look at the sky, the stars will be there. The same stars that have been there for every generation of human beings that has ever looked up. The same stars that provided the first evidence that the universe was full of light, that the cosmos was a place of warmth and structure and presence. And they are still those things. The stellar era is not over. The universe is not dark yet. The galaxies are still visible, still sending their light across the void, still maintaining the impression of a cosmos that is rich and full and alive with the energetic processes that define the middle age of any universe. But the impression, as this investigation has shown, is always partial, always a surface reading. The universe that appears full is mostly empty. The structure that appears permanent is temporary. The galaxies that appear stable are slowly being separated. The stars that appear eternal are burning through finite fuel. The light that fills the night sky is a brief, local, thermodynamically expensive phenomenon in a cosmos that is predominantly dark, that is becoming darker, and that will, after a duration of time so vast it cannot be meaningfully imagined, be darker than any darkness that currently exists anywhere in the observable universe. That is the universe, not the one that comforts, not the one that reassures, not the one that offers a reason or a direction or a meaning proportional to its scale, the one that exists, the one that the physics describes, the one in which the voids grow, the expansion accelerates, the galaxies separate, the stars fade, the black holes evaporate, the entropy increases and the silence deepens, the one that began in fire and is ending in something that makes fire seem, by comparison, impossibly warm and impossibly close and impossibly, briefly alive. The one that is mostly nothing was always mostly nothing, and is becoming with every passing moment more perfectly and more completely nothing than it has ever been before, and will, in the end, be nothing at all. There is a specific moment that happens to some people who spend long enough with these numbers. Not a dramatic moment, not a sudden revelation accompanied by any particular feeling of awe or terror, just a quiet shift in the way ordinary things appear. The coffee cooling on the desk, the light coming through a window in the afternoon, the sound of wind moving through trees outside. These things do not change, but something in the frame around them changes. The frame that usually holds them, the frame of daily life, of personal history, of human scale and human time, becomes briefly transparent, and behind it another frame appears, larger, much larger. And in that larger frame, the cooling coffee and the afternoon light and the wind in the trees are visible for what they also are: thermodynamic processes, small, local, temporary conversions of low entropy into high entropy, occurring in one particular corner of one particular planet, orbiting one particular star in the outer region of one particular galaxy, during a brief window of cosmic time in which the universe happens to be lit. That second frame is always there. It does not go away after you have seen it. You learn to hold it alongside the first frame, the human one, because you have no other choice. You cannot live entirely within the cosmic frame, and you would not want to. But the knowledge of it changes things in ways that are difficult to articulate and impossible to unfeel. The universe is very large. It is very old. It is mostly empty. It is growing emptier. And you are in it, briefly, made of its matter, powered by its thermodynamic gradients, capable of knowing these things about it, and utterly unable to change any of them. This is the condition the physics describes. Not hopelessness. The physics is not interested in hope or its absence. Simply condition. The condition of being a temporary arrangement of matter in a universe that produces temporary arrangements of matter, and then, by its own laws, dismantles them. The condition of being a local decrease in entropy in a universe whose total entropy never decreases. You exist, in the thermodynamic sense, because somewhere nearby, in the core of the sun, 93 million miles away, a nuclear furnace is converting hydrogen to helium and releasing the energy that, after traveling to the surface of the sun, and then across space, and then through the atmosphere, and then through biological systems of extraordinary complexity, ultimately powers every thought you have ever had about any of this. And that furnace is finite. It has been burning for roughly 4.5 billion years. It will burn for roughly another 5 billion. After that, the particular thermodynamic subsidy that makes complex life possible on this planet will end. The sun's death will not be the end of the universe. It will barely register on the cosmic scale. The sun is one star among approximately 200 billion in the Milky Way alone, and the Milky Way is one galaxy among hundreds of billions in the observable universe, and the observable universe is a fraction, possibly a vanishingly small fraction, of the full extent of space. The sun's death is, in any objective accounting, a minor local event, but it is not minor to the things that depend on it. And the pattern it exemplifies, the finite fuel supply, the gradual exhaustion, the transition from burning to cooling to cold, is the pattern of every star in the universe, every single one. The sun's fate is the universe's fate, expressed on a smaller scale and an earlier timescale. What makes this worth sitting with is not that it should produce despair. The physics does not prescribe an emotional response. It does not suggest that the correct reaction to the universe's thermodynamic trajectory is grief or acceptance or defiance or anything else. It simply describes what is, and what is this. The universe produced complexity. It produced stars, and from stars it produced chemistry, and from chemistry it produced biology, and from biology it produced minds, and those minds looked at the universe and found it beautiful and terrifying and vast and strange. And the universe, indifferent to all of that, operating entirely by physics, driven by gradients and fields and the relentless mathematics of thermodynamics, continued expanding, continued cooling, continued, in its patient and total way, heading somewhere that minds cannot follow and beauty cannot reach and terror loses its object. The minds are part of the universe. This is not a trivial observation. The matter that makes up every human brain, every neuron, every synapse, every electrochemical signal that constitutes a thought, was forged in the cores of stars that lived and died before the solar system formed. The carbon in human cells was fused from helium in the interior of a massive star, under pressures and temperatures that would vaporize any familiar material instantly. The oxygen dissolved in human blood was scattered into space by stellar explosions billions of years ago, and gathered into the molecular cloud that eventually collapsed to form the sun and its planets. The iron in human hemoglobin was produced in the final moments of a supernova, the last synthesis possible before a star tears itself apart. The atoms of which a human being is made have existed in one form or another since the Big Bang. They have been part of interstellar gas clouds and stellar interiors and planetary surfaces and oceans and soils and biological organisms before becoming, temporarily, part of a human being thinking about the universe. And after the human being is gone, those atoms will go on, scattered back into the environment, incorporated into other systems, eventually dispersed into the larger flows of matter that cycle through the galaxy. The atoms will outlast the person. The galaxy will outlast the atom's current arrangement by an almost incomprehensible margin. The universe will outlast the galaxy by a margin that makes that incomprehensible margin look small. This chain of containment, person inside moment, inside civilization, inside planet, inside solar system, inside galaxy, inside universe, is ordinarily felt in the direction of diminishment. The universe is larger than the galaxy, which is larger than the solar system, which is larger than the planet, which is larger than the civilization, which is larger than the person. At each step outward, the previous level becomes smaller, less significant, more contingent. The person, at the innermost level, appears infinitesimally small, and they are infinitesimally small, measured in light years. They are infinitesimally brief, measured in giga-years. They are thermodynamically negligible, measured in entropy. And yet, the universe does not know any of this. The universe does not know its own size, its own age, its own entropy, its own direction, its own composition. It does not know that it is mostly empty. It does not know that its voids are growing. It does not know that its stars are finite, or that its expansion is accelerating, or that the cosmic microwave background is cooling. It does not know what dark energy is, or why the proton has the mass it has, or why the initial conditions of the Big Bang were as extraordinarily low entropy as they were. It does not know anything. It is not a knowing entity. It is a physical system, governed by laws evolving according to those laws, containing no internal experience of itself, except in one place, except here, except in the small, temporary, thermodynamically expensive arrangements of matter that developed the capacity to model themselves in their environment, to build internal representations of the external world, to reason about causes and effects, to ask questions and search for answers, to look at the night sky and feel something, to calculate the future of the cosmos and find it unsettling. In those arrangements of matter, in minds wherever they exist in the universe is briefly aware of itself, briefly, temporarily, without any guarantee of continuity or any mechanism for permanence, but genuinely, undeniably, the universe, through the improbable elaboration of its own matter, achieved self-knowledge, and then, by its own physics, it is in the process of dismantling the substrate on which that self-knowledge depends. This is not melodrama, this is physics. The self-knowing matter of the universe, whatever form it takes wherever it exists, is made of atoms, powered by thermodynamic gradients, dependent on stars, constrained by the finite supply of low entropy, and subject to the same cosmological fate as every other arrangement of matter in the cosmos. The minds go out with the stars, not at the same moment. Minds might, in principle, persist long after the stellar era has ended, finding other energy sources, adapting to the cooling cosmos. But the minds go out eventually. The thermodynamic gradients that power thought are as finite as any other gradient. The universe does not make an exception for self-awareness. It does not recognize consciousness as something that deserves preservation. It proceeds by physics, and physics does not care what it is processing. There is a specific version of this that is worth stating plainly. The human mind, or any mind of comparable complexity, is the only known mechanism in the universe for the universe knowing itself. There may be others. There probably are others, somewhere in the 200 billion galaxies of the observable universe, each containing hundreds of billions of stars, each potentially hosting planetary systems, some fraction of which may have developed chemistry capable of the kind of complexity that produces self-awareness. The numbers are large enough that the absence of self-knowing matter elsewhere would be the more remarkable outcome. But none of those minds, if they exist, are accessible to us. They are separated by distances that light takes millions or billions of years to cross. Some of them may already be beyond our cosmic horizon. Some of them may have existed and gone extinct before the solar system formed. Some of them may not yet exist. The universe of mind is as fragmented and isolated as the universe of matter. Islands of self-knowledge separated by vast, mind-free voids, with no communication between them, no shared project, no accumulated wisdom that passes from one island to another. Each island of mind knows what it can observe from its own position. Each is limited by its horizon. Each is subject to its own thermodynamic context. And each, when it develops the capacity to calculate the universe's future, arrives at the same conclusion. The lights are going out. Not quickly, not violently, but finally. The process that produced minds, the long thermodynamic chain from Big Bang to stellar nucleosynthesis to planetary chemistry, to biological evolution, to nervous systems to self-reflection, is a process that the universe runs once per region of space, or perhaps a few times, during the window of the stellar era. After that window closes, the conditions for the process do not recur. There is no cosmic cycle that resets the entropy, restocks the hydrogen, relights the stars, and gives the universe another run at producing complexity. The second law of thermodynamics does not allow resets. Entropy does not decrease. The window does not reopen. This is the hardest part of the physics to sit with, not the size of the universe, not the emptiness, not even the time scale of the heat death. It is the finality, the one-way character of thermodynamic time. The fact that the universe's brief experiment in complexity, its remarkable, improbable, thermodynamically expensive production of structure and light and life and mind, happens once and then is over. The matter disperses, the energy dissipates, the entropy reaches its maximum, and the universe enters the long, cold, eventless state that, in terms of physical time, will constitute the overwhelming majority of its existence. The stellar era, for all its brilliance, for all its complexity, for all the extraordinary things that happen within it, is a brief exception in a history that is mostly characterized by the absence of any such exception. The universe before the first stars, and after the last black hole, is a universe of unbroken, featureless expansion. The stellar era is the flash between two darknesses, and we are in the flash. We are in the flash, and we know we are in the flash, and we know the flash is temporary. This is perhaps the most unusual position any arrangement of matter has ever occupied. Inside a temporary phenomenon, aware of its temporariness, capable of calculating both its beginning and its end, and unable to do anything about either. The flash does not last longer because it is observed. The observation does not slow the cooling. The knowledge does not alter the physics. The universe does not adjust its thermodynamic trajectory because something within it became capable of noticing the trajectory. It simply continues, and the noticing, the remarkable, improbable, unrepeatable noticing, continues for as long as it can, inside the window that the physics provides, and then it does not continue anymore. There is no way to end this investigation that resolves the discomfort it has accumulated. The discomfort is the point, not the discomfort of something going wrong, not the discomfort of a solvable problem or a correctable misunderstanding, but the discomfort of something being true that does not align with the scale at which human beings naturally think and feel and assign significance. The universe is not scaled to human concerns. It is not interested in human concerns. It produced human concerns the way it produced everything else, by the operation of physical laws on matter and energy over time, and it will unmake them the same way. There is no external frame within which human significance is guaranteed. There is no mechanism in the physics for the preservation of what the physics produced. The universe makes minds and then moves on, and the minds, while they last, do the only thing they can do, which is to look at the stars still burning in the night sky, to look at the galaxies still visible at the edge of the observable universe, to look at the cosmic web still intact, still structured, still encoding in its filaments and voids the gravitational history of the cosmos, to look at all of it clearly, without the comfort of a story that makes it end well, without the reassurance of a framework that places human existence at the center of cosmic significance, without the softening of a conclusion that suggests the universe has a purpose proportional to its scale. To look at it for what it is, a vast, cold, mostly empty, temporarily lit, thermodynamically finite system that happened in one small region during one brief era to produce something capable of looking back. The looking back is extraordinary, not in the sense of being cosmically important, it is not, but in the sense of being improbable, intricate, and real. To go from the quantum fluctuations of the inflationary epoch, to the density variations of the primordial plasma, to the gravitational amplification of the cosmic web, to the formation of stars, to the nucleosynthesis of carbon, to the chemistry of living things, to the neuroscience of perception, to the mathematics of cosmology, to the specific act of understanding what the universe is and where it is going. That chain of causation is so long and so contingent and so unlikely at each step that its completion here, in this temporary window, is genuinely remarkable. It does not save anything, it does not change anything, but it is remarkable, and what it reveals, at its end, is not comfort, it is not a reason, it is not a purpose that the universe was aiming at when it produced the conditions for self-awareness. What it reveals is the universe as it is, ancient, vast, mostly void, expanding under the influence of a dark energy whose nature remains unknown, built on a scaffold of dark matter that cannot be seen, lit by stars that are burning through finite fuel, organized into a cosmic web that is beautiful and temporary and already beginning, at its largest scales, to dissolve. A universe that began in conditions of extraordinary low entropy and has been spending that endowment ever since, heading toward the maximum entropy state in which nothing happens and nothing can happen, and the concept of an event loses its referent entirely. Go outside tonight. Find a dark place if you can, away from the light pollution that modern civilization casts upward into the sky. Let your eyes adjust. The stars will appear gradually, then more fully, until the sky looks the way it looked to every human being for most of human history, full of points of light, more numerous than can easily be counted, arranged in patterns that generations of people named and navigated by and built stories around. The Milky Way, if your sky is dark enough, will appear as a pale band crossing the sky, the combined light of hundreds of billions of stars, seen edge on from our position within the disk of the galaxy. The Andromeda galaxy will be barely visible to the naked eye as a faint smudge if you know where to look, 2.5 million light-years away, the light arriving at your eye having left that galaxy before any member of the genus Homo existed on this planet. All of that light is old. Every photon reaching your eye has been traveling for years or decades or centuries or millions of years. The star you are looking at when you see Betelgeuse is showing you what Betelgeuse looked like roughly 700 years ago. The star is not guaranteed to still exist in its current form. It is a red supergiant close to the end of its life, and it may have already exploded in the supernova that will eventually come for it, without our knowing yet, because the light from that explosion has not had time to reach us. You are looking at a past that may no longer be present. You are, in a very literal sense, looking at ghosts, at the light of things that may or may not still exist in the form that produced that light. The entire night sky is a palimpsest of different times, superimposed on a single moment of perception. The near stars are recent, the far stars are ancient. The galaxies at the edge of the observable universe are showing you a state from billions of years ago, a state so early in cosmic history that the universe barely resembled what it looks like today. To look at the night sky in full knowledge of what it is, not a fixed dome of lights but a three-dimensional, temporally complex structure in which depth and time are the same dimension, is to look at something that cannot be fully held by any single act of perception. The eye sees a flat sky. The mind, informed by physics, sees a four-dimensional history of the cosmos projected onto the retina. The two images do not fully reconcile. They do not need to. They are both real. They are both inadequate. The flat sky full of stars says, "You are here. It is night. The world is large and dark and lit by ancient light, and this has been true for as long as your kind has existed and will be true long after you are gone." The four-dimensional history says, "You are here briefly, in a cosmos that is mostly empty and growing emptier, during a thermodynamic window that opens once and does not reopen, looking at light that has been traveling toward you for longer than your civilization has existed, from sources that are themselves temporary, in a universe whose ultimate destination is a silence so complete that the concept of looking will have no referent, and the concept of you will have no substrate, and the concept of briefly will have expanded to encompass everything that ever happened, and compressed it into something that, against the backdrop of the heat death, is indistinguishable from nothing. Both of those things are true simultaneously. Neither cancels the other. The warmth of the present moment and the cold of the far future coexist in the same physical reality, separated only by time. But time is not nothing. Time is, for anything that exists within it, everything. The fact that the universe will be cold and empty and eventless in a Google years does not make the present moment cold and empty and eventless. The present moment is warm, if you are warm. It is lit, if you are under stars. It is full of the texture of being alive in a universe that is, right now, still doing the extraordinary things it does during its stellar era. The physics does not take that away. The physics simply contextualizes it, places it within the larger frame. shows you what surrounds it on all sides and in both temporal directions, an immensity of nothing, briefly interrupted by something, and then nothing again. The interruption is real. The nothing is real. The relationship between them is what this investigation has been about from the beginning, from the first description of the cosmic void between the galaxies to the final state of maximum entropy that the universe is building toward. The relationship between what exists and what does not, between structure and emptiness, between the temporary and the permanent, and the conclusion that the relationship yields, followed honestly to its end, is this: the nothing is more fundamental than the something. The emptiness is more native to the universe than the structure. The silence is where the universe came from, in the sense that the pre-stellar universe was dark, and the silence is where it is going, in the sense that the post-stellar universe will be dark again, and the lit interval between those two darknesses, the interval in which stars burn and galaxies shine and minds look up and wonder, is brief, cosmologically brief, brief in a way that the word brief was not designed to capture and cannot fully carry, and yet, the brevity does not make it nothing. This is the last thing the physics says, and it says it without comfort, without intention, without any suggestion that it matters. The brevity does not make it nothing. The fact that the stellar era is a temporary window does not mean the things that happen in it are not real. The fact that the universe is mostly empty does not mean the parts that are not empty are illusions. The fact that the cosmic web will dissolve does not mean it does not exist now, structured and intricate and billions of years in the making. The fact that the light goes out does not retroactively darken the time when it was burning. The physics is not nihilism, it is description. It describes a universe that is real in its present state and that has a future that is different from its present state, and it makes no judgment about the comparative value of those states, because physics does not make judgments about value. The judgment about value is something that happens only inside the window, only in the brief interval of the stellar era, only in the small, temporary, thermodynamically improbable arrangements of matter that develop the capacity to find things valuable. And those arrangements, the minds, the self-knowing matter of the universe, find the universe valuable, find it beautiful, find it terrifying, find it worthy of attention, find it adequate ground for the full range of responses that complex nervous systems are capable of generating. The universe does not share this assessment, but the assessment is real and it is occurring, and it will not occur again after the window closes. This is the position, standing in the window, knowing it is a window, looking out at the light that is still there, knowing what the light is and what it is doing and where it is going, unable to stop any of it, unable to slow the expansion of the voids, or refuel the aging stars, or reverse the growth of entropy, or recover the information already swept beyond the cosmic horizon, unable to do anything about the physics at all, able only to know it, to understand it, to stand in the brief warmth of the stellar era and look clearly at a universe that is mostly cold, mostly empty, mostly dark, and entirely indifferent, and to find, in that looking, something that feels, despite everything, despite the scale and the time scale and the thermodynamics and the accelerating expansion and the growing voids and the cooling background and the fading stars, like the most important thing any arrangement of matter has ever done. The voids are growing. The universe is cooling. The expansion is accelerating, the stars are finite, the entropy is increasing, the silence is coming, and right now, for a little while longer, there is still light.